So I'll just, okay. Thank you all for joining. Yeah, we have Christian Emery Taylor, who has been here now last time, and we had a conference called, International Conference on Fundamental and Applied Sciences that was held in Istanbul, Turkey. They had a hybrid conference, Boston, Istanbul, but we presented oral virtually, and we had a special session they granted us. There was a chair of the session, and everything went very well. But we couldn't record it, so we are going to uh, try to present that here, and that's what I'm going to present briefly what I presented there, so you can get an idea of what was going on there. Um,
So we'll just go in the same order that we did last time.
yeah. So let me see why it is not coming up. The entire screen should come. Let me see.
And then if there's time, Christian, if you have anything you want to show us as well, that'll be.
Yeah.
Or there'll be time for.
I would take the chat option to ask to you, Christopher, to not to interrupt anyone in the flow. So should anything agree?
Oh, once it's on, yeah, no problem.
Okay.
Can you see now?
Yes, small as usual, but it's now it's recursive. Yeah. Okay.
So let me see whether I can.
You have to remove the frame of the, so just the plain paper would be, yeah, that much bigger.
Thank you. It's coming now.
That's good.
Is the screen coming up? Let me see.
It's perfectly readable for me.
Okay, let me see. Let's see. Previous. Try to. I have to get the. Okay. I have to get my lab. So, bottom one.
The second menu from top you were in.
Was it on? I'm not able to see that correctly.
It was.
When I press this thing, is it coming on? Oh, let me check again. Due to some reason. Okay.
This was a good example of one of my older non-theories that what you search for, your eyes see, but your brain can't recognize. So when you're searching for a menu back, you will read every other of the 15 menus, but not back.
Oh yeah, it's a Murphy's law kind of thing. Sometimes. So I don't know whether this will help. Oops. Oh, that's not what I want. I am having that. Let's see. Share screen. It used to work very well. So now it's kind of showing up. Strange thing. That's not what it is. Okay. I know what the problem is. The one that I want is not coming up.
Take your time, Roger. It doesn't have matter many more.
It's coming up, anything?
Yes, thank you. Now we're back for
yeah. Is it showing now? It's okay? So I can just stop subtitle. I don't want subtitles. All right. So you can see right now. Okay. So this was the presentation in the ICFAS, which I said the International Conference on Fundamental Applied Sciences. That was 11th International Congress in Istanbul, Turkey. We had it from July 9th to 11th, but our presentation, special session presentation was on July 10th, and we were given special session and we could make it into special on physics. This was online with myself, then Christopher and Emory. We had presentations. So we will present briefly what we presented there because we couldn't record there. So it is about rank n tensor physics. It's a time tensor that I found, so I'm continuously deriving from Iyer Margulis model, as we know, the point physics of 0 point and the micro black hole. And it's all coming out to be quite correct. And then I kept deriving to higher levels, and then finally reached uh, which I presented last year. So the review is about the algorithm. Again, I'm going to go into details even here because there's a lot involved, but the reference will give an idea of how the formalism developed. So this reference quantum physical, which is like a few references after the Iyer Margulis in physics and Astronomy International Journal. So this is an Oriental Journal of Physical Sciences where I developed the formalism. It's essentially a modified Newtonian, kind of like modified Newtonian mechanics, but I remove all the constants, and the constants are creating problem because realistically all the constants, even the Hubble constant or Planck constant, everything is and especially universal gravitation is not really constant over a period of time. They change, so they are not really constants, and that's creating a lot of problem, when you do the physics. So I want to remove all the constants. So I did general transform using Legendre, Fourier, Laplace, Laplacian, and also whenever necessary, Lagrangian, and all the kind of formulation. I know that I had to do that to remove it. Also, the mass aspect. The mass is another one that's creating problem, as we know, Yang-Mills theory, the mass gap and all that, dark matter, dark energy. All these problems are, really creating problems. So I want to remove all that and define everything in terms of time domain. That's where the first step. The first step is make everything in terms of the spin, rotation, revolution, and and then make everything as a function of time. So these are very complex equation, but essentially I put it the x and y. Y is essentially then the scalar field, which is like eventually like light and sound, but at the quantum level it'd be like vibration or photons and things like that. So this is the thing that showed that the universe is actually working like a black box. So we are trying to poke into, we are getting some signals, or we are trying to get some signals, poke into that thing, and then peak. So poke and peak type of thing that we use in the, even IT basic programming, similar thing is good. So that's what we are. So depending on, we have to look at different perspective and then see coordinates and see what we are getting, and try to figure out what is in the black box. That's essentially what we are doing. So when you do that and then do inverse, this is very interesting things happen. When you do inverse transform, I can get a 4-vector matrix of in time. So, and that looks like this with the proper time, real time, global time, local time. This is again rank 2 type matrix, although it is more, closer to rank 1, rank 2 type of thing. And that's a function of the transforms. And again, these formulas appears in theoretical experimental design. So this is the next derivation, next step to get into time tensor form, like 2 by 2 matrix. Again, it's a 2 by 2 matrix. And when you look at that, we can actually convert it into the time as a 4-vector matrix. We can represent as rank 1 uh, vector type. So it's a 4-vector, so we can do vector. So it's actually a bra vector, and then the ket vector will be the gravitation gradient. Again, the question of gravity and is a big thing. It is the one that has totally unresolved yet. So we are trying to do quantum gravity type of thing. But what is gravity? What is the role of gravity? It's actually a gradient. It's not really a force. And that's what many of the physics is showing, that it's not a force. Many of the physicists are agreeing that it is some interaction that's going on. That's all we know. So it's produce some gradient in the form, and that can be the ket vector. And when we combine these two, something is happening. I don't know why I'm not getting the. Okay, this particular one is not coming up. I have to reload it, I think. But in any case, it's just a Schwarzschild matrix. So the idea of gravity is that it can couple. Okay, it can couple with the time, but it may not interact. If we couple with time, it's like a sensor. It's sensing. So the gravitation is sensing there is a time. Time is sensing there is a gravity. But both are just in the sensing. They are not interacting. But the interaction depends on many few conditions that we are trying to figure out on the metrics. The time, if we interact, the time tensor will curl inwards. This is what see, and then very high gradient, like in black hole, supposedly. Again, black hole is again in quote unquote. We are not sure that such a thing really exists completely. Right now, it shows that it is, uh, but it will curl the time tensor inwards, and so the interaction starts, and we get scalar fields out of that. So of course, math is involved in that. So to understand that, we are just progressing one step at a time. So we understand that, and then when we do the expanded matrix, it is like the 4 by 4 matrix. I'm not able to show here. I don't know why it's not coming up, but sometimes it doesn't come up. The 4 by 4 matrix is very similar to the Schwarzschild matrix. And as we know, the black hole thing is derived from Schwarzschild matrix. And one of the solutions in the 4 by 4 matrix of the Schwarzschild is what is really went to the idea of black hole and the black hole physics and everything. But the rank 2 need extension to rank 4. And the reason is that uh, we cannot describe with the rank 4 anything about quantum aspect. So we have different domains like quantum domain, mesoscopic domain, and astrophysical domain. It's like going into a microscope. So even the materials I studied, we see certain things, but we go let through the microscope, we see fine structures within uh, grain boundaries or grains and all that, and even further dislocations and all that. So very similarly, in quantum, if we go in further, the quantum level, we see many exotic things, as we know. And the same way, in the astrophysical level, is like a scope. We see the night stars, some point stars gleaming, and the planets not blinking, not hardly visible. But when you go to telescope, we see more structures within, very active structures, including magnetars or quasars, galaxies, and so on and so forth. So we need more than just rank 2 to unravel that. So the current theories cannot really account for the observed phenomena, even with the standard model and everything complete, because there is question of dark energy, dark matter, and all that. So one of the reasons is that we are using a combined domain, like space and time together. And there's a problem of units there. Space has one type of unit, time has another unit. How do you mingle those things? So the Mengosi space time has a problem of units. And I find, for me, those are very important. Those fundamentals are important, and we have to be consistent. And at some point level, it is becoming a problem. And we see inconsistency between quantum and the general relativity, famous Viking catastrophe. Uh, so ultraviolet catastrophe, which is a problem classical physics, quantum physics said they solved that, but the problem again came up with the vacuum catastrophe. So we have the different domains of realities we have to consider. So this is something we have to reconcile to. So in the case of time, we are, in our time, we are using scalar time, mathematic time or scalar time. When we say it's, 9 o'clock here, it's just a scalar time. But is it the real thing that's happening? I think time has more aspect to it, and that's what we are considering. And when we transform, uh, the domains, space, everything into time domain, we simply consider, for example, translation. So translation x, y, z. We resolve any vector r. Let's say r vector, which represents. So if I put r and theta, I have just the two aspect, right? There's the two uh, rank aspect there. But when I consider when I in the quantum level, we have to consider different directions and everything, and they are not really communicating. Uh, so we have to consider X, Y, Z separately, uh, and that group theory especially requires that. Now we'll look into that more. So initially we'll try to use the translation coordinate. I like Euclidean, convert everything to Euclidean because that's what we are used to, and we can do it on a paper. So even toroidal, even it's 4-dimensional, we had converted Euclidean, and we have XYZ, and then you have rotational coordinate. And then we consider only one rotational coordinate, in this case theta, and then even we consider that we have to use rank 4. So XYZ theta, I can write it as mu nu alpha beta. So we are already a rank 4 tensor. And this formalism appears in Maynard Mary's last year's, you know, uh, reference on algorithm IT in, again, OJPS, Oriental Journal of Physics. So I give brief formalism of that. So some of the highlights of that, uh, this rank 4 has a 4 indices, 16 components, and it can describe stress energy tensor, electromagnetic tensor, Riemann, curvature tensor, etc. Again, I am going to go into details about that, but I will touch upon some of the aspects a little later on. So if we consider that rank 4 tensor, I can write into, you need a matrix here. So that matrix I had assumed equal to 1 as a unitary one in my you know reference, in my formalism. I didn't consider this metric because normally we consider many other metric like c square equal to 1, things like that, general relativity uses, and sometimes h over c is considered equal to 1, things like that. So very similarly, sometimes the metric is, we can consider unitary, but when you go actual manipulations, we need this metric. And then as a fourth derivative of the action. So action is the final aspect, as we know that Yang Mills, all the theories finally try to
Excuse
describe
me.
themselves
Sorry,
action,
which
because
slide are you
action
on, Rajan?
is nothing but the
Sorry, Rajan.
integral of the Lagrangian. Yeah.
Rajan, which slide
Yes.
are you on?
You have, yeah. Oh, you cannot see it?
No.
Okay.
Well, which slide are you on?
Sorry.
Yeah.
The fourth one. Are you still on the first one?
Yeah, we're still on the first
It's
one.
not moving? Sorry. That's the problem with this thing. Okay, I have to stop sharing here. Let me see. Thank you for letting me know. So I think, like you said, I had to go back to the other screen, the entire screen. That when I do that, let me see whether it comes up. Anyway, by the time I had to reload this one because it doesn't show some of the things. Okay. So I had to anyway reload that. So let me reload that. Hopefully, we'll be able to. Right. So I am going on. Okay. So I have to briefly go through this again. I think. Anyway, I'll try to see how we can accommodate that. Okay. Yeah, I think this is okay. This is better. But hopefully, I'll be able to. Let me see. I can go here. When I do this, does it come back to?
Yeah,
Does it
that's
show
better.
the? Oh, okay. So now it's moving, right?
Yeah.
Okay, good. Thank you.
You've got like 8 minutes left. So
Okay,
continue
sorry.
from where you were.
So I may have to start all over if you don't mind.
Okay, yeah, you can
Briefly.
do that.
Anyway, I'll try to hurry up, but I may need extra 10 minutes, 5 or 10 minutes. So
And
I'll briefly
extra,
go through that again.
right.
Yeah. Sorry for the slides. It was not moving the way it should have. Okay, so rank and tensor, as you know that. So this is a review I briefly mentioned about the previous work, and you know, this is in my okay. So I'll just show the reference that's at the bottom, the OJPS that gives the formalism and gives a scalar field as a function of the rotation, which is since the time domain. So when I do the inverse transform, I get that 2 by 2 time matrix, which again appears in the myself, Malauer and Taylor theoretical to experiment. So it gives more details on that one. And now the rank 2 tensor again. Now it shows uh, can be written in terms of uh, bra vector of the time. And the gravity, like I mentioned in my talk, in my audio without this slide, that the gravity is actually a gravitational constant gradient. So that's how this probably is coming up. And then the interaction, the coupling and interaction creates this particular density configuration, which is like a 4 by 4 matrix. And this is the Schwarzschild matrix. And this is where the black hole thing is coming up. If we solve this one, the vacuum, we get a black hole effect. It's black hole singularity. So this is an artifact of this metric, I think. So we don't know it. But that's how the black hole physics started coming up. In any case, so I mentioned that we need a rank 4 because now we convert into the translate in a quantum level, everything is split up. So we have to consider XYZ separately and rotational coordinate. So we get rank 4. Again, this occurs in my reference, which is algorithm IT or JPS. And that goes into details about this rank 4 time tensor, which I give in this one, in that formalism, I take this as equal to 1. So essentially, for derivative of the action in terms of the space-time coordinate, x mu to x to power of beta is a space-time coordinate in the domain. And then when you equal to 1, this translates to that. But we need the metric in order to do further manipulation. But I can also decompose this particular matrix into the 4 submatrix, which gives the quantum domain T00KL. The action is minimal, time is reversible because of the tunneling effect, things like that. The time is uh, reversible, degeneracy of energy and things like that, which makes it the time reversible. But only at the quantum level that's reversible. So the question of time machine going back in time and all probably relates to this quantum aspect. But the mesoscopic, we know the time is asymmetric. It goes the event. And submatrix astrophysical domain is the action is maximal, time is again hidden there. So again, so these aspects are coming out, and it explains a lot of things. I'm not going to go into details here now, but also TIJKL helps us to define the supernominal domain, and we believe the supernominal domain is something we have to really consider. But the action there is infinite, and time is imaginary, and that may be how the dark energy, dark matter comes into picture. Because if the light is moving, in that case, may not be light, but it could be some wave that's moving faster than speed of light. Then we cannot see it, so that appears a little dark. So that makes sense. It's a dark aspect, and that may be all around us. In fact, uh, so that's one of the things that's coming up with all our research. But the action is defined as an integral of the Lagrangian over time. Lagrangian gives the equation of motion, the action, and everything. So then we can define in terms of using Legendre transform, we can convert into Hamiltonian, which is the main thing in quantum physics. Whereas the astrophysics consider more Lagrangian aspect, the general relativity. So Lagrangian, momentum, position, and Hamiltonian all come into picture there. So now I can convert this action into Hamiltonian, like that one, using this definition. And then we can talk about a curvature, extremity of action, things like that, space-time. So those come into picture. And we can convert to Levi-Civita symbol. As we know, we cannot deal with the rank 4 in the normal situation. We cannot do it on a pencil and paper, on a paper. We have to convert to rank 2 to get a matrix that can be represented on a paper. So Levi-Civita symbol it also helps to convert all the energy, momentum, angular momentum, and the entropy into the time variable. So they have their own metrics, and one of them, the angular momentum, has a rank 4 vector. Again, we can reduce it using rank factorization and things like that I will consider a little later. But if the metrics are equal to 1, we get this Levi-Civita aspect, which in the theory of everything and all, they talk about these. But I am not there yet. This is the first aspect. So arithmetic and algebraic time then are important, because arithmetic time is what we are using, and all the classical physics uses only that. But it can do the mesoscopic things, the motion of planets, oscillation of pendulum, radioactivity, that we see. They are all good enough. The arithmetic time, scalar time is good enough. But if you consider quantum aspect and even astrophysical aspect, we need these time as a tensor. So as we know, the scalar is rank 0, vector is rank 1, and tensor is anything more than rank 1 is a tensor of matrix, the matrix form. So effects of gravity, inertia, everything, we need this stuff. So again, conservation law, which I am emphasizing on that, and I'll briefly mention a couple of things about conservation. That conservation is very important to understand the physics. Conservation of energy and momentum. Realistically, only at the collision, the classical physics choice, and also later on, the real conservation of energy and momentum occurs there. But all of the things, if you want to extend that, right now we are only the correspondence principle for quantum physics and equivalence principle for general relativity. So the conservation law, but in the case, if you do the time tensor, it conforms to conservation law. So we know the famous Lagrangian, even for classical physics, the Lagrangian doesn't change with time, is 0. And Hamiltonian is constant. And same way, the time tensor is constant. So that helps in the conservation. As we know later on, that invariance and things like that come into picture. We need this kind of relationship. Now, rank 4 even is not enough, surprisingly. So, because we consider quantum entanglement, wormholes, parallel universe, uh, and other aspects, we need rank 6. The rank 6 tensor, however, we can convert to lower ranks by using Tucker decomposition, matrix factorization. Now, we know that in IT, they use TensorFlow and things like that. And the flattening of ranks are important to do data processing. So very similarly, in the physics also, we need something like that. So the rank 6 can be defined in terms of, again, it's a matrix that ensures that the rank 6 is there. And then get defined in terms of the derivative of the Euler angles. Euler angle, again, briefly, let me mention, I'm going into detail, is very important for anything moving, like gimbal or uh, other aspects or gyroscope, things like that. So the Euler angle keeps track of the geometry of that. So very useful phenomena. So we use that and the derivative of that with respect to time needs domain. So domains of reality becomes important. So that we consider even in our discontinuum physics, different types of realities. But in this case, in terms of the time coordinates, are different in each direction. So it takes into account that aspect. And then when this metric is equal to 1, they will simply define that. Again, I'm actually publishing, it's almost done. It's in the stages of Galilei proof, and it should be appearing anywhere, anytime. The quantum gravity time tensor that appears in Physics and Biophysics Journal anytime now. So that gives the formalism. Again, why we need rank 6 again is because, as we said, the translation XYZ, but you have to also consider the rotations in different realities, as spherical rotation or three-dimensional rotation of theta, phi, and gamma, because we have then spin, and then you have the rotation of like the electron around the nucleus, that's a rotation. Then the atom itself is revolving around in the molecular motion, that is revolution. And this, if we go to electromagnetic aspects also, we give scenarios about when we need all this stuff. So we need a rank 6 there, XYZ theta, which is written IJKL, or like Penrose and people like that are saying the Nobel laureate that we should probably use ABCDEF, but that's something that is coming up. That's the convention. The quantum space, mesoscopic environment, astrophysical level, we can all now do that. And then factorization of the rank from rank 6 to rank 1 using this particular factorization aspect, U1, to get components can be used. So that helps to convert to meaningful operations in our pen and paper, that thing. So we can do 2 indices. And then finally, group matrix. Okay. So this gives, just a schematic that I'm going to use right now of how things happen in a general sense. So we have supernominal level that's happening, but it's noisy. So we cannot detect anything. It's like dark aspect. But if we consider this as a condensate, general condensate, evaporation process will create a 0.6 signal, and condensation process will create a distorted field, and so you have quantum form type of thing, vacuum back. Again, it's in the initial stages of development, so I'm not going to go into details. But we can have an equation like this, an algorithm. This noise in quotation means it's a distorted field, and then you have a signal created. So the local distortions happen because a random process can create local distortions, like vortices, things like that. So that is what this is. So again, that is sufficient energy you can create sufficient to create a scalar space-time. That's how the real aspect starts coming in. And then we can use this Riemann and the Euclidean geometry. We can go back and forth using these aspects of the algebra. So we have geometry and algebra there. Then, in general, what's happening here is that the longitudinal wave, in general, you can consider the local level, it is becoming vorticing into a transverse wave. And then we have point singularity. So actually, the Schwarzschild thing should be a point singularity, not necessarily a macro singularity. So that's why it could create micro black holes. That's what we consider Iyer macular system. The same thing, micro black holes, and then you have the 0 points there. So again, it goes back there. So it's self-consistent, the whole thing. The whole modeling is self-consistent. But these micro black holes probably can combine. That's a possibility. Accretion can occur and create a macro black hole. That's something we have to really look into later on. But we can do a group operation. And again, today I'm not going to go into detail about using umbrella model and everything to understand the physics and the quark and things like that. And another time I will go into, because I think I am running out of time now. But then we can define the time loop, things like that. We are in a time loop of 80 years, which is like the Halley's Comet and things like that. In another presentation, I will go into details. So in summary, basically, we highlighted the previous ones for rank 2, and then showed that is similar to Schwarzschild matrix. Then we went to rank 2, and then we derived a lot of important things, especially the conservation laws, things like that, expressed in terms of Leibniz symbol to characterize the physical quantifiability in terms of energy, momentum, and entropy and things like that. Then we said that we had to go into rank 6 to define completely the quantum mesoscopic astrophysical level. And then we come to the idea of point singularity and things like that, and space-time, how the space-time can form from a noisy superluminal quagmire. So ongoing, we are going to look into the cosmic gravity. I'm already developing quantum gravity, loop quantum gravity, things like that. Beyond loop quantum gravity, actually, I have come up with an equation that will solve the problem of, at least in theory, question of gravity, which has not been, people are not able to account for. 40 plus articles we have altogether, and then quantum form and vacuum back. Then we have the question that about that Christopher, working with Christopher, and about using the hyperspace aspect to combine with the time tensor aspect. Then Titsonium physics with Emory Taylor. And so a very specific project could be Titsonium physics, spatial temporal tensor geometry. That's one of the important things that comes out of that. Again, these are additional references apart from what I have shown there. And then we have, that was a presentation, the ICFAS. So thank you very much. So I'll open to question and then whatever we need. Should I keep that on or?
Yeah, I think so.
Okay. So I'll keep the thing on.
Yeah, just so
you can
people
see that now.
review.
Okay. Okay. You can see that now, right? Okay.
Yeah.
It's moving. Okay. So I wanted to show it's moving. It was not moving before. Okay. So yeah, you can go ahead and ask me questions, and then if you have time, or you want to go ahead, you want to finish question and answer now, and then move on to your presentation, or you want to present and then move on and do our.
Well, no, I mean,
question and
does anybody have any questions? Emory might be that he's gone, but So it's like, I mean, I'm interested in the transform. It's on this second slide, is it?
This one? Okay.
Yes, because so it
Yeah,
seems
you had
to
an
me.
excellent question. Yeah.
Oh, if we go back, yeah, this one. So
Okay.
what is the input? You said it's time, is it?
Yeah.
Okay.
Yeah, time.
And
The
then you
time
have
is
all these.
input.
Sorry, what?
Yeah, the time is the input, but it is a catch-22 or what you call a feedback circuit. Because the time we are inputting here is the time that we measure, which is a scalar time. You see that?
Okay.
So we start with, it's like trial and error, like Newton-Raphson method. I did something called numerical analysis, and I program it where you start guessing, like you use equation and then rewrite the equation such that I like to use the function from, like, you have x squared plus x plus 1, right? So you express equal to 0. So you put x equal to, let's take the square root. So you put x square equal to minus x minus 1, and then take the square root, and then try to solve that problem, right? So why start with x equal to 0. So you get some value, the new value of x, and put that new value of x into the right side of the equation, and you get updating the value until
Okay. So it's not
supposedly
time necessarily. It's this x plus 1 term or something.
Yeah. So x is the input, where you, if you know the rotation angle at any time, like you try to get an estimate of the rotation. For example, a spin, right? Spin can change in time. So you put spin as a function of time, and you try to find a function for that, right? You try to regression. You do a regression analysis. So you can get data as a function of time, right? So you put that function here, and then you have the again you do a regression. You do many measurements of the rotation of the electron, supposedly around the nucleus. In time, it changes. So you get a function for that, and that function you put it in there. And same way, revolution of the whole atom as a function of time. Again, the regression analysis will give you some function, and you put these functions into this one. So they are all function of time, right? So you have this. This is your Fourier. Then you have your Legendre. You have, this is the Legendre. This is the Fourier. So you put these functions, and you get a value of x. That's input value. And then you measure the scalar field for these conditions, and put that scalar field. So you put x and y plot. So you get a certain graph of the x and y, right? So this shows that this graph has to be, and this is made, it's a metric graph. This graph has to be a linear. It has to have a linear plot, which means it has a slope and intersect. So we get many points, right? And this one shows that it has to be a linear plot. So then we put a linear plot to that, and then see how the spread is, what the variance is, sigma values, and see whether they fit in. If they don't fit in, it kind of flags. It flags there is something wrong in the measurements, or if something is not correct. So we do this to get a check on how things are working.
Okay, so
your
input is x or something, and then
X,
your output is what this graph. But then, so the question I have is, you know all of the functions inside, you know your input value, you know your output value.
Yeah.
So how is it a black box? Wouldn't it?
Well, this is okay. suppose I am looking at the electron, I am looking at certain perspective. I have certain coordinate, certain system I am using, right? I'm looking at a specific way. I'm looking at atom at a certain angle. So I'm looking into the atom, for example. I'm probing that with either a radiation, alpha radiation, or anything like that, or use a spectra or J spectroscopy, different types of spectroscopy, which helps me to figure out what the spin is and things like that. So I'm looking at a specific way of looking at things. Okay, that may not be universal. That may not be necessarily universal, but I'm looking at a specific things. I'm looking at certain angle, certain perspective. I have certain perspective of that,
Oh yeah.
depending on the coordinates. Yeah. So, but I look at some other system. Suppose somebody is looking, alien is looking for somewhere else, right? And looking into the thing, they may not see like that. An observer in a far distance may see that totally different. So depend on the observer. It's observer dependent to some degree. That's what I'm
Yeah,
saying.
absolutely. Because
Because
if you measure the spin of an electron, let's say, and you
yeah,
get spin up, but then the next time, but then that removes the data for left and right. But then if you were to measure the left and right, then you'll lose the spin up. But then it seems like in your that introduces a slightly different issue though, because it seems like in your maybe not, but in your equation here you have spin and you have rotation the same time, but you can't know both at the same time. Is that right?
Heisenberg. I mean, it could be true with the Heisenberg thing. That's the other problem. So we may be changing the domain. See, that's why you have to use time tensor. Okay, this is the first level where and as we know that the what we can measure is this one. But that may not be really true because we are looking at spin at one domain, and then we are looking at that's exactly I'm saying rank six. The rank six we consider that aspect. So the spin we are considering one domain of reality, whereas when we are talking about rotation, we are talking about another domain of reality. You see that? So they are not really matching. The same problem with like Emory Taylor has pointed out that we have done the falsification of special relativity is because of this particular aspect. Because the coordinate system is not consistent, it's changing. So we are looking at something and then looking at some other domain of reality and then say what are same, but they're not the same. So that's the
okay. Very
problem.
interesting.
Yeah.
Okay. So are there any other questions?
Yeah, I just have a small one with respect to ice-based theory, as usual, because that's my domain. Ice-based theory, for those like Emory that might have no contact with, or our viewers, is a theory is able to predict geometry and exact values by exact integer geometry of relations found between dependencies unknown so far on constants of nature. And the question to Rajan is with respect to his time variables, being they now in a matrix or not, could you assume or think about these could be fully discrete, as the recent discovery by space is that we indeed have a quantum of time. And that quantum of time in iSpace IQ units, which are not by any way human artifact poisoned, they are really based on things like golden ratio pi and 1/6961 prime integer to be the quantum of time. So would that be the case, that really everything is Lego style discrete? Could your matrix math made compatible to that you would get a different frequency of clock ticks when you want to represent a typically continuous changing time, as is done in relativity or this general matrix continuum-based mechanics? Can you think about such a consequence? Would that be proven true experimentally, let's say, that really quantum of time exists? How would that relate to your idea?
Yeah. So that's an interesting. Thank you, Christina. It's a very deep thought. Yes, actually, I'm developing, like I said, but I don't know whether I can show it now. But in any case, it's a further development of this rank 60. So now I develop from this one into and look in the matrix and then say that how the time and gravity. Now I use this one uh, to combine to show about a short seal, but that is for rank 2, for this one, for 2 by 2 matrix. But what happens when I use rank 6? What happens to that? So that's what I'm considering. And when I consider that, interesting thing comes out. And essentially, as you know, the loop quantum gravity says that the space-time is discrete. It's not really continuum. So if you use time, the time becomes like a wave vector. So any time, like in the future, that's why we cannot, what is happening in the future is the time is appearing as a wave vector. Because when you are rank 6 means that it's not a scalar. So it's a vector, it's in the vector form, and the gravity interacts with that to create scalar aspect. So it collapses. It collapses the wave vector. So it's a quantized. It's actually quantized. So the time is. So I'm showing how to scalarize the time, how to scalarize the gravity, because that is very important. Scalarizing separately the time, scalarizing gravity separately is important. Then you put them together, we get the equation of motion, the Lagrange. We can define the Lagrange. An interesting thing about Lagrange, I'm going to publish another paper a few months, once I finish this formalism, is that the Lagrange, finally Lagrange, depends on the energy p square over 2m minus whatever the potential energy is. That's the Lagrange. But what I'm finding is that Lagrange in itself we have to define as a function of uh, m uh, m which is mass, time, and space. So they are different. So the mass what mass I am getting? So the mass again is appearing as a tensor. You see that we have to now abstract everything. So mass, how does the mass come in the picture? Like generality says that mass bends the space time, right? Curves the space time that you get gravity. But where does the mass come? So I'm questioning. Those are all in question. That aspect of the gravity, because the gravity itself is a gradient, like I said. So the mass comes from the superluminal thing, and it creates, like I say, in this one, uh, in this one, the mass is created by this process of the signal, which is a local level thing that's happening, distortion, like a discontinuum field that we are talking about with Emory, discontinuum physics. It's a discontinuum energy field that we are getting essentially out of this point singularity. So this discontinuum thing is what is creating the space-time, and that's a very fundamental thing. And this space-time is not a continuum, because the wave function when it collapses, as we know, is quantized. So it's quantum. The gravity is also a gradient. So quantum. So the mass we get is not quantized. So the mass is a quanta that we get out of it, and that there is no time without mass. So if we put in the Lagrangian, we need to have mass to have time. Because time doesn't exist in this superluminal thing. When the mass exists, time exists. The mass goes away, time disappears. Uh, so the discontinuous energy field, there is no real time. But so the scalar time that we talk about comes about because of this particular interaction, which is a quantum interaction. So hence, it's not occurring continually. It's discontinuous. So which means that the time has to be quantized. Which so again the time will have to be quantized, it's not continuum. The scalar time, because it's so small, it could be Planck time or anything. So this space-time that we are talking about, the scalar space-time, will be in that mid level a Planck scale, at a Planck scale, right? It's created a Planck scale, because anything below the Planck scale, it cannot exist as a particle. It probably is a quasi-particle, or it could be a what you call as a unparticle, or whatever it is called. So like hot PDP mechanism says that it could be an unparticle, and then through the mechanism, So this could happen in this singularity, the hot PDP mechanism, and that creates the particle. And this particle has a minimum dimension. And we believe, like with Emory, that is a discontinuum length, which is many orders of magnitude than the Planck scale. So actually the time is Planck time, but actual space is much larger. So anything below that, like 10 to the power minus 26 or so, I think we calculate, Planck's time times the speed of light, which gives about 10 to the minus 26, maybe the smallest space that is required for a particle to be observable. So that's in the observable universe, but that is quantized.
Rajan, while I still here like you that the time in your model is quantized over some rotational vectors and the matrix arrangements.
Yeah, actually that's correct.
Theory, the high-space spacetime and high-space theory comes from the electron and strictly from the electron and is way distant-wise away from Planck regime. It is about 10 to the power of 9 times 10 to the power of minus 19 seconds, 10 to the power of 20 hertz, and hence is an electron intrinsic, if ever experimentally proven, which I hope, because there is a new quantum core clock, which will be 1,000 times more precise than current quantum time clocks.
Okay.
So the current quantum clocks is in the regime of 10 to the power of minus 17, 10 to the power of minus 18 hertz, routinely by current time standards at the moment in the lab. And recently, a year ago, have been found a critical frequency, which we were searching for 25 years in an element, I think thorium it is, thorium-223 or something like that. And once that frequency is in place, there's a super interesting resonance there, which allows a thorium to be a quantum core clock. And that instantly, more or less after you have 10 years of lab regime to get that running, of course. But from the theory, it says it will be 1,000 times more precise. And what iSpace theory predicts is they will see for the first time experimentally that time as we know it in the lab will not go beyond iSpace spacetime because the electron and its geometry intrinsically has a maximum frequency of internal rotational elements, which is simple in the relation of golden ratio ampere to the iSpace spacetime forming the electron charge. And hence, unless someone is able to relativistically squeeze golden ratio from golden ratio to 1, I see no way how the time of an electron will go beyond this frequency predicted by iSpace. And hence that when you have a frequency comp, you can see that the colors of the frequency comp go up by each 1,000th of factor when you take a center spike of a frequency comp, where has been given a Nobel for, by the way, and make that the next center for the next second level frequency comp. And now there is just a necessity of a third level frequency comp going into the frequency range of iSpace theory exactly. And that comp will be only on the left hand. It will be comp wise correct on the left side until iSpace spacetime is reached and then drop to 0 because no more time from an electron at least point of view to be generated. If iSpace theory is wrong, and that is what it would make it falsify, the interesting thing is if the quantum core clock would still be able to create higher frequencies, then iSpace theory would still hold for electron regime, would be a theory still correct for constant of nature within electron shell regime, but would not be the core of physics. And then it would be interesting to go on, probably even down to Planck level, as many theories like yours, Rajan, suggest. But when iSpace theory has something to say, then there is no Planck regime. It's just all in the brains of theoretical physicians. And it's physically impossible to reach that frequency ever. And that's important to state either that ideas are also just that sometimes in the brain and not in the lab. And I want to see that in the lab.
Well, and the actual measurements, there may be a limit. Like you said, I agree. These are theoretical. What I mean, say, even in the theory, even theoretically, right? Even if I suppose I can go only up to Planck scale, I cannot go beyond that, which means that it is intrinsically quantized, even theoretically. But the actual thing is
quantized by Planck is this right? But iSpace theory is when you have really the time to have a look on iSpace relations for Planck regime constants, and there are plenty of them. then you see they're not primary. Primary is golden ratio ampere. Primary is 1/6961 I space second. Primary is the number 1 in the term of 1 plus 111, 111 plus 1 given the electron mass as an integer. Anything subprimary. And everything else is just mathematically constructed from, well, Planck equations. And Harbour C over G is a Planck equation giving an extremely large expression with an integer geometry of golden ratio of 6 times pi to the power of 10 times a lot of human artifact-induced factors. And once you leave SR unit system, these drop to 0, or to 1, better to say then, and eliminate from the equations. And what stays is quantum mechanical true geometric things directly visible in I-space IQ unit system. Trivial as that. And hence I-space theory has already proven that there is not many human artifacts in the SI system. There's only a single human artifact in the SI system, and that is time-based. And that's why this quantum of time makes the thing so interesting. All artifacts in SI, including meter and kilogram, are time-based and not kilogram and meter-based. And I've proven that.
Okay.
Yeah.
If there's,
I just wanted to comment on that, but it's still very interesting. Thank you.
Yeah. Okay. Not only that, Christian, one more thing I just want to add, that this is, I remove all the constants because of what you said. So actually, I'm not considering any calculation here, but I'm saying even if we say that is Planck level, even then it's quantized. But see, you see that I don't put numbers here because I have not yet calculated the constants, because it wouldn't make any sense to calculate the constants without completing the whole theory. And when I do that, maybe it will be something like what you're saying, like attosecond, things like that. Maybe the lowest level we can go. Maybe a limit to that. And also, let me put it that way. That's the last one I want to add. In the case of fermions, there is no, they cannot, like, unlike photons, they cannot interact, they can go into each other, which means that each movement of the fermion has to be separate in space. So that automatically quantizes. So it means that there is a minimum, you cannot have continuous angle of spin, for example, or rotation or revolution. So there may be a specific level that it moves from theta of one angle, then it moves to the next quantum level, like that. Actually, I calculate separately.
It's
I have to
quantization like I do in iSpace, actually. It's not by input, but by definition of the geometry itself, by output.
Yeah. And that calculation comes later, but so I think, but I'm just pointing out. Yeah. So let me get out of here, and then probably Christopher, you can start. Let me get out of here.
Okay.
I think, yeah, okay. So is there any other question? Otherwise, Christopher, you can start doing your presentation.
Okay.
And we can always, look at discussion later on. So there's no.
Okay, so can you see this?
Not yet.
Not yet.
Oh.
Thank you, Christopher.
Okay.
Emory.
Oh, yes. Had this problem before. Okay. Maybe that, yeah, that's better. So I'll hide that. And then. Okay, so the title of my talk is, all right, let's start. Oh.
Nice image.
There we go. Okay, so the title of my talk is Anamorphic Universe Model Hypothesis. So the objectives of this talk are the introduction of the anamorphic universe model, overview of support vector machine analysis of hyperspheric boundary, excuse me, alternative methods of measuring hypersphere size using a 4D wireframe sphere, and scaling of the hypersphere to fit the Hubble parameter, or constant if you prefer. The elliptic curve 1728y and the relationship of that to the expansion rate of the universe, and the periodic lattice of the same elliptic curve and its tori. We'll also look at 3D elliptic curve and the relation of that to its to particle masses from the standard model. So to begin with, we'll just look at the transform, stereograph, 4D stereographic transform. And this takes the, so if we have the coordinate values for the galaxies in right ascension, declination, and z redshift, then so that would be the x, y, z coordinates. And then we can convert those into 4D coordinates. And so that's projected onto a hypersphere, which is then rotated and scaled by a factor of 70. So we'll see later. So that's essentially what these do. That's the transform there. So the rotation, so here we have the galaxies projected onto the hypersphere and then rotated. And then this is where the scaling factor comes in, which is the factor of 70. So if we were, this is the blue dots here in this graph are the untransformed galaxies. And then, so we're suggesting in order to fit all of the galaxies inside the, inside this circle here, which is the first Great Wall, the sphere needs to be rotated by 180 degrees and then shrank by a factor of 70. So then the idea is that to reverse that, you need the factor of 70, which is also close to the Hubble parameter, but I'm not sure if that's really related. The reason why it's probably not related is that the purpose of the model is, or hypothesis is to, it describes redshift in a completely different way. So instead of it being about recessional velocities, instead it's more, the idea is that it's more about sort of distortion that occurs when projecting from the hypersphere onto the tangent space. So here we have a point A on this longitude line, and point B here. And then when we project them onto the hypersphere, we get A1 and B1. And obviously the distance between these 2 points is greater on the tangent space than it is on the hypersphere. And the further you go up, the more that difference will be apparent. So yes, so it's that distortion that is causing the redshift, and that's why redshift gets more intense the further out we go. Here's just a graphic illustration again of same process, but using the 3D coordinates. So projecting off a 4D hypersphere. And then we have the untransformed galaxies in red and the transformed galaxies in blue. So for the next section, we'll look at support vector machine group, hyperplanes, and decision boundaries. And the way this works is we have two classes. So in this case, the green dots here would be the untransformed galaxies and the red dots are the transformed galaxies. And then, so between these two classes, we can create a decision surface using the support vector machine model kernel trick, which is described by this equation here. So yeah, the idea was that if we were to find the decision boundary between the two different classes, we might also therefore capture something of the radius of the hypersphere. So initially, we discovered that the hypersphere radius was just outside of the first Great Wall of galaxies, which was interesting. And those are calculated using the recessional velocity distance at about 432 megaparsecs. But obviously, if you change the C parameter of the SVM, you're going to get smaller or larger decision boundary. But C1 is the general one that is accepted, so sort of a baseline. So this is interesting. So initially, when I wrote the paper for this conference, we had this distance then as the distance, the radius for the outer hypersphere, which would in turn have made the distance for the hypersphere in 4 dimensions to be 14.4 megaparsecs. But more research was needed to ensure that this was correct. And so another method maybe of confirming or denying it was to use a 3D sphere wireframe, but to create a 4D graphic projection of that and to use it to determine the size of the hypersphere radiuses. So here we see a 3D wireframe, and then I sort of tried my best to create it in 4D and project it back over the galaxies. What we find is that the inner sphere does, you know, fill up towards the first Great Wall, and then the outer sphere then sort of contains the bulk of the galaxies before they begin to diffuse outwards. So this seems to suggest that the decision boundary that we captured initially was not the outer, but the inner sphere of the hypersphere. So this changes our calculations somewhat. You can see here how stereographic projected 4D hypercube, you know, and this is the equation to generate that. But how basically, if we have the distance to the outer vertices at 86.4 megaparsecs, then basically we've just doubled everything. So the distance to the hypersphere will be 28.8 megaparsecs instead. So this has a knock-on effect then in a variety of different ways. Basically, as we can see here, the revised measurements, we've got a radius of 28.8 megaparsecs, diameter of 57.6, but possibly the most important value would be the surface area at 471.5 gigaparsecs cubed. So yeah, that's one way of doing it. But an alternative method might be to use, let's say, so instead of using a hypersphere, we could use the Hubble parameters. So we'd just be looking at the exact measurements for redshift, recessional velocity redshift. And so the interesting thing about that is these equations were the initial ones I used to do that. So basically we're trying to expand the hypersphere so that our projected galaxies line up with the Hubble velocity. But I've been doing a bit more work on this, and I found that these equations aren't exactly correct. So we start with the Lorentz equation, transforms, and then create the distances for that. So then we have the max distance, and then we're going to vary the diameter of the hypersphere. And what we find is that, let me see. So then we modify all of the galaxy coordinates, and then we have our diameter with our the new diameter for the projection point. Then we do a distance formula and get the basically we're looking for the hypotenuse value. But this isn't, I don't think this is correct, because we also need to then, we do one transform onto the hypersphere, then we need to transform back off and then do these calculations. And when I've tried to do that so far, it's basically failed. So I don't know what the problem is, but oddly enough, we predicted it would converge at 4,320 megaparsecs. And when I did that using the early method that I was just speaking of there, that you can see, it converges around 4,326.5 megaparsecs. So that is, it's about 91.4% if we were to use 4,320 megaparsecs instead. But so that would be the diameter of the hypersphere. But all of those values need to be rechecked. And in any case, all of those measurements are based on recessional velocity in one way or another. So in order to do it properly, I mean, obviously this is going to give us different values for the surface area, which are much greater, nearly 200,000 teraparsecs cubed. So, but the better idea would be to calculate the diameter of the hypersphere based on the redshift alone, but more precision is needed for that. So instead, we'll look at elliptic curves and modular forms and the expansion rate of the universe. So in 1875, Edward Lucas challenged his readers to prove that a square pyramid of cannonballs contains a square number of cannonballs only if it has 24 cannonballs along its base. And right, so the solutions, he's correct. Size from trivial ones, it is the number 24, and it gives us 70. So see a relationship here between the number 24 and 70, which I then, so normally we see that in, let's say string theory, bosonic string theory, where we have 24 spatial dimensions, and then in the Weyl vector we have this number 70 for the time dimension. But here we're flipping that because we know that 70 is important in terms of expansion rate. So then 24 is important, so the expansion is obviously related to space, but 24 is related to time. And then we ask, well, when we think of time and the number 24, the most obvious sort of delineation is, or division is 24 hours. So based on this, the idea is that the universe expanded in one day, and creates this kind of curve based on the cannonball problem. But we can also formulate that in terms of a Diophantine equation, which instead of a discrete curve like we saw earlier, it gives us a smooth curve, which is actually an elliptic curve called 1728y. So if we were to take this elliptic curve on face value, it appears that there was a full start before the universe began in earnest, and we can also look at different expansions. So this is, roughly the proportion of the universe at hour 1, hour 2, hour 3, and hour 4, and where it intersects, and it would just go on up for 24 hours. And then we can plot these as the Weierstrass form of the same elliptic curve. Gives us slightly different coefficients, and then from that we can create the modular form, and infinite hyperbolic tilings of the same. So see the various conductor that goes into that, the discriminant, and the Sato-Tate is SU2. So there might be some relationship there back to fermions or string theory and even the multiverse maybe. So, but we're not going to look into that today. Instead, we're going to look at the relationship of particle masses to the tori of the elliptic curve 1728y. And within that, there's going to be 3D elliptic curves and some string theoretic concepts. So to start this process off, we use period lattice for the elliptic curve 1728y, and again we use the Weierstrass equation with slightly different coefficients in this instance, and then so when we have that, we can create two different elliptic curves, tori out of these using that equation there, and then we can select one of those toruses based on some conditions that I won't go into here, but then we expand it using 3D stereographic projection, and then we take a cross section. So you can see there's a kind of a figure 8 here and a handle. So if we take a cross section through the center of the 8, then we get this ellipse. So using string theoretic concepts where particle masses are equivalent to the diameter of the torus is, the ring diameter is can be calculated then using the equation to find the perimeter of the ellipse that we saw in this slide. and setting the mass of the electron for the baseline where we cut through here. So then we're expecting that because the elliptic curve expands then out towards infinity, that we can slice at different points, like where this black line is. And then if we move that black line back and forth, sorry, we will like hit upon different masses for the different values of the particles in the standard model. So that's what this graph represents. There's a blue line in the background, which is the continuous masses. You can see it here better. And then the other lines just show where the points where the different particles in the standard model are located. So obviously the electron is at 0 degrees radians. The up particle then is at 1.22, and the neutrino or the down quark is at 1.59 radians. And then you can see the tau neutrino and the tau. Here's just a kind of a close-up on the strange and the muon, because they're quite close together. And then we have strange and the muon again, then the charm at 1.6 radians, and the tau, and just a slightly different view of that again, zoomed out with the tau neutrino in it. So this is the list of most of the particles of the standard model with their respective degrees and radians of rotation on the 3D elliptic curve. Now, yeah, so what's missing from this is the top and the bottom quark, which appear to lie outside of the range of the simulation I created. So either I will have to expand the simulation or use some sort of linear regression model on this. So we see the electron here at the bottom, then the up, down quark tau, and it goes up to the tau electron. But you know, we could extend it using some linear regression model. These are just different examples. So again, we have the electron here, and if we think of this as the sort of the torus, then this is where the up is positioned. These are the different radians and up to the tau. And then we'd have obviously the antiparticles on the other side. That's the concept, perhaps. Another way to graph these is to use the pairwise differences between the masses for each particle, and then, or the radian pairwise distance differences. We've seen this strange in the muon again is kind of an anomalous in the fact that it's so low. We could think of these maybe as well as it starts going up, but yeah, there's a kind of a curve there, but then this curve is probably more interesting. But really, there's not a whole lot I can say about this point. Maybe when it's extrapolated further and includes the top and the bottom quark, there might be something more to say about it. But yeah, it was more just to see what would come out of it and sort of the technical challenge in doing it as much as anything else. So in conclusion, the hypothesis is that the redshift of galaxies is caused by a stereographic projection from the hypersphere to the tangent space. The universe is scaled up by a factor of 70 since its creation. This scaling occurred within 24 hours. As SVM model gives 43.2 megaparsecs for the radius of the inner hypersphere, which we said was 28.8 then for the total size of the hypersphere. But yeah, and so the wireframe, 4D wireframe appeared to confirm those measurements. But as we said, the true measurements can only be obtained using the Z redshift alone, because the sessional velocity redshifts are being called into question here. So yeah, so we can also define the expansion rate of the universe using the elliptic curve 1728y, and the 3D elliptic curve of 1728y can be created using stereographic projection to then calculate the string theoretic mass measurements for the rotations or for the standard model particles. Okay, so that's it. Hope I'm still.
Oh, great. Good job.
Thank you.
Thank you very much. Very refreshing theory from my point of view. Very, very novel and genial. If I may have first and a very simple question, or let's say a remark. One of the first pictures you showed up was showing a square of a value which was a circumference in your model. And that, if I remember properly, was up to the 4-digit precise with the I-space predicted Hubble constant derived from exact quantum values. And if that would be a related case and you have a circumference and half a diameter, then your model would be exactly off by 2p from the predicted I-space value. And that could be interesting for you calculating backwards when you say, we have to tweak that to find where the Hubble might be, just as a feedback.
Okay, so if I just share the screen again, just to see.
You have to quick feed forward to the presentations. It was one of the first 2 or 3 which you showed, where some values were on.
No,
go ahead. Probably was in the shortly after that.
Am I too far?
No, go on.
Okay.
No, this is too far. Yeah, here we are. We have circumference 13.5921 gigaparsec squared, and I-space has exactly 30.59 megaparsecs per kilometer per second as the age of the universe, or not the age is a running constant, of course, but this is the visible, reachable range of the light cone, which is visible in principle by theory of relativity. So that means this is not really an accident when you hit a cosmologic value to 4 digits. I think that is interesting and should be taken the time to do a second calculation backwards. And what would it be? Would you have that taken not as a circumference, but as a diameter? I mean, geometry and string theory is a lot of assumptions, and that is just another assumptions. I don't want to do numerology here. It's really just it is that
that's very interesting. Yeah,
this should be taken serious because many of the I-space things were accidentally looking, and when I deep checked, it weren't accident, and that's what makes things interesting.
Yeah, well spotted there. I did notice something about 13.8 kind of pick up, and it works because it's a gigaparsec value.
I'll give you the exact value. I have it here in Mathematica. Let me give you the exact value. Exact value in frequency is 2.331441793, and when you have the natural one, EH0 cosmologic N, you get 71.993829, which gives the age of the age of universe or something. I don't remember my own variable names, forgive me, but I can look it up in the paper easier, just to tell you exact value from a numerical value, what I expect here. Once I brought it up, we should clarify that in a minute. Deriving H0, here's the paper, and it says the cosmologic age calculated is 13.591012 and so on. Yeah. I paste you the exact value in the chat. They have something to play with. But of course, you can always look at my papers to have the exact quantum geometric value from I-space theory in geometric form as input to your own models, of course, which is very helpful. As I told, I-space is not a TOE. I-space is a physics tool usable as a telescope into macrocosmos, but with exact relation and usable at a microscope into nanoscale or lower, with a perfect microscope and telescope at the same time. And that makes it so special. And used as a tool, it can tell you what your theory might be geometrically of, because when you would derive that from a differential equation, you would have an exact number, but you didn't know why you have that exact number in the end. And when you look in the quantum-related I-space things, and you have a clean thing, there's so many times to the power of electron mass multiplied with so many times Planck constant divided by electron charge over classical electron radius squared times fine structure constant to the power of so-and-so, and then you get that value, and that makes it a non-numeralistic value. It makes it a quantum geometric one.
Yeah, it's interesting because if I use a different value for the Hubble parameter, I was just using you know, the natural logarithm of 2, which is around 69 point something.
Very, very late. You just need to calculate backwards. That it is, it's not forbidden in physics to do that, to have cross-checking.
Yeah, I mean, calculate it backwards because, I mean, I did already kind of calculate it forwards. So, you know, calculating backwards will just bring me back to the beginning, I guess. But
I'm not in your shoes, so
yeah, fair enough. Okay, so are there any more questions or?
Yeah, I just a brief thing about see, a parsec is about 3.6 light years, right? Something like that.
Oh, is it a trillion light years?
Tell you exactly what a parsec is because I have it in my file.
It's a lot.
It's defined. It's defined, and it's an integer definition, arbitrarily done by SI committee. So numerically, a parsec per meter is 1 over 30,856,000,000,000 meters per parsec.
So light years in terms
meter
of light
value,
years.
yeah, 30 trillion, yeah. Okay. Yeah, that's
in terms of light years, I think it's about 3.6 or something like that.
Oh, okay, yeah, light year value might be different.
I put it in the chat again that you have it what it is exact, because it is about the distance to a radius behind Pluto, and that makes it so stupid because it is really a stupid definition, because no cosmologic measurement will ever be able to be exactly somewhere behind Pluto, which is quite good for distances in our solar systems, but is a complete bullshit when you go to the end of the universe, because even if you handle that precisely like ICFAS theory does, it's still an approximation to be compensated. If you go in the 6, 7, or 8, 9, 10 digit, 1 digit up, you're kilometers away from that precision you would need from a quantum level. It's not the parsec as such is wrong, but you should stay in the inverse of the frequency of the Hubble constant, which is exactly defined in quantum level. And when this frequency, we can also give you, the frequency value is lossless forth and back convertible, and is to the power of -18. I'm not sure how that will go off when I do that here in the chat, but I think you get the idea. Yeah? So, and that is exact, and that's it. Yeah, that is Hubble exact and frequency from ICFAS theory. Arbitrary number of digits, if you wish.
Okay, yeah, that's interesting. I didn't realize that about the parsecs, and that sounds like
so
a bit of a
human artifact bullshit, as is the ETBH. So the so-called ITBH written like that is a ICFAS spacetime human artifact factor identified in the definition of time of SI unit system itself, and it goes like that. You have golden ratio ampere, which is the quantum of ampere, and multiplied with 1/6961 ICFAS second, which would be a different unit system. So you have to give my word for it that this is a sweet spot, that golden ratio ICFAS ampere is exactly the same than golden ratio ampere. There is no difference in these two unit systems. So when I multiply golden ratio ICFAS ampere and just call it ampere times 1/6961 ICFAS second, then I need a factor ITBH, ICFAS spacetime human artifact factor, and that is technically 47 times 14.66487 over 10 to the power of 24. So this is a really large value, but this is not physical. This is purely an artifact of SI unit system. And depending on if you have electron charge, you have to multiply or divide that out by power of 1, because you have ampere second. So the second is 1 exponent. So you drive the ITBH out by power of 1. In the case of Planck units, you have volt ampere second squared. So you have to put the ITBH by the power of 2 out. In the case of the electron mass, is volt ampere second to the power of 3 over square meters. So you need to put the time correction to the power of 3 out. And if you go to the gravitational constant, I found it's to the power of 8. And it's always the same time. It's 1/6961. And hence, I'm absolutely sure time is quantized in 1/6961 units. And that makes I-space theory not the theory to predict constants of natures with a magic number 6961, but with an identified quantum of time to be 1/6961 I-space seconds, what makes it very much physical.
So Rajan, did you ask your question?
Well, so the question is, the nearest light year or the parsec, what is it, in terms of what are the planets like Alpha Centauri, or what galaxies or constellation does it encompass? Your 4,000 something of megaparsec. What is the outer boundary? Is it a galaxy or constellation or all the observable universe?
Oh yeah, it's an interesting question. So with the well, if you're talking about the 4,320 megaparsec value, that value is meant to be the let me see, is the I believe it's the radius of the hypersphere. So yeah, it is the radius. So that value is just in the 4th dimension. So it's not a distance that we can travel. And anything on the surface of the hypersphere could be projected to infinity on the tangent space. So the value of, let's say, 2 times 4,320 megaparsecs, is a let's say we could travel that distance, from one pole to the other of the hypersphere. But you'd never be able to travel the distance from the South Pole, let's say, to the end of the tangent space, technically, because it's too far away. So in a sense, the projection from the hypersphere, while the hypersphere is finite and we can make measurements about how big it is and whatever, on the tangent space, all that goes out the window. Everything can be, you can be talking about infinite distances. However, yes, this is so part of the thing that we're trying to do is to kind of like figure out the size of the hypersphere by using either structures within the universe, like the first Great Wall and that big bulk that I showed you, or other methods. So that was the 4D wireframe method, and then using the recessional velocity and trying to get a match. So yeah, it's interesting that we had 43.2 megaparsecs for the inner radius, and then when we tried to get a match with the Hubble constant, we projected 4,320 megaparsecs. So, which is just the first one multiplied by 100. So it seems like there's some weird harmonic going on that allowed that to occur. So whether that's the correct, if that's the correct value, well and good, but it seems unlikely for a variety of reasons, and certainly, well, it would completely disprove the Ohm hypothesis in a way, but on another level, then also because, why would the recessional, if the Ohm hypothesis is correct, then the Hubble recession velocity is incorrect, and then the fact that the value would be the exact same as the hypersphere would seemingly be very improbable, But yeah, so it is interesting that we get this harmonic, and then also, like Christian pointed out, that there seems to be this other harmonic then with the circumference, which is technically an area rather than a line in this case, to be equivalent to, or in some way harmonic with the age of the universe.
The circumference, then I was wrong. It's just the combination of an error is then probably then just a 4-digit numeric entity. Then I wouldn't have brought it up. So
yeah, I believe it's an area, because yes, because in a 4-dimension, right, a circumference would be an area. That just seems logical. So, but I mean, anyway, that with certain new measurements from JWST and elsewhere, it looks like the age of the universe could be pushed back by like twice what it is. So maybe 26, I think, go to.
Yeah.
Yeah. So it is
20 billion. 26 billion.
Yeah, he suggests that. But with the current model I have, it all of that is sort of irrelevant, because if you have a problem with your theory based on the observations you're getting from your instruments, you can just it's like the theory's been disproven, but you can just alter the theory, like, well, the universe is just older than we thought. And then the next time you get a better measurement, you have to push it back further and further. But with the Ohm hypothesis, basically it predicts infinite redshift values. So there will be no end to this age of the universe problem, and you cannot determine the age of the universe then from the redshifts, because it would give you an infinite value for the age of the universe, which is obviously not correct. Okay, so is that it for questions? Because then we can move on to Emory's presentation. Great.
Emory? Yeah, we can follow up later on. Yeah. Emory,
no
so you can have enough time for
a quick introduction to Emory, maybe, because I don't know him yet. So what is his background and so on? So that doesn't need to have self-introduction.
I think Emory is going to introduce himself. He's going to give a brief overview of who he is. I mean, he did that in the last text meeting, but I think, Emory, will you be able to give us like 10 minutes, 5 to 10 minutes of your vitae, so to say?
10 minutes?
Or 5 or 2 even.
10 minutes. You can talk about yourself.
Anytime switch, just because I had this great introduction from Emmanuel when I was presenting first on tech. So
yes, that's a fair point. I think if anyone's going to handle the introductions, it should be Rajan. But if Emory wants to,
I will give like 1 or 2 minutes. But I think Emory has to himself. So Emory actually is a amateur astronomer. Oh, something happened.
Yeah, you're good. You're just solo.
Okay. So Emory is actually a amateur astronomer, but he has also done some art and things like that. But he got interested in physics much earlier, and he has attended top physicists, Nobel laureates, and he has given lectures in MIT and Harvard on various aspects of general relativity and quantum physics. And he has, when we started, he contacted me, and because he saw the thing, and he had contacted many other people, but he said that he didn't get any proper response from them. But then we got hooked on, and then he started looking into. So he does thorough research. Let me tell you about Emory, and he has sent me the whole aspect of Newton that I didn't know, the inner details of Newton and everything. He has sent how the Newton came into, all his theory and everything, because that's important, because that is still that we are looking into about gravity, universal gravitation. Of course, Galileo was there before, but he said that, as we see the papers, the falsification of general relativity, special relativity especially, because we are considering, different domains and coordinates that doesn't match. So, and Einstein himself, according to Emory, he had done the thing, and then I went to that, and it makes sense that Einstein himself falsified himself the last time because of this quantum experiment he was considering. That I think Emory is going to talk about that Q2TE. That he will talk more about that. But essentially, Einstein was conducting an experiment there. He started doubting his own, continuum theory. So, and then the quantum aspect also, Heisenberg and Bohr's experiment, there are certain faults that we have brought about the Bohr's interpretation. How the quantum aspect come into being is the questionable thing. So we are recalculated everything, based on the fields. So he thinks that there are different domains of realities. that there is a mathematical reality, there is a physical reality, there is a there are three other types of reality. He will be talking about that, and he has always made into a table called table of realities, and in that one he considers the scales and then also what realities exist at each level. So it's all a lot of it is in our minds, but they are not really their physical reality. What we measure is different from what we can see that what it is. Like time, for example, maybe an example of that. So when you look at all that, he has compiled the whole thing and on different scale levels that we go from astrophysical level, the bottom level to top level, then we go into in the quantum level, and then we see one of the consistent thing that we see is a discontinuum length. So that's the smallest measure we can make, and we are not exactly calculated that, but we are estimating what it is. And so he's going to talk about mostly about this table of realities, and so he has done different types of things, and of course, he may not talk here. He has done some, spy work and things like that, which we are not talk here. But he has, he has exposure to different areas of physics with the real people, real scientists. That finally he has come to this understanding that many of them are not, the final or fundamental theories, but they are, a consequence of that. So the higher theory is the discontinuum physics, and finally that will be the top level, and from there you can derive other things where we talk about discontinuum energy field, which is like it replaces Higgs field, it permeates all of that, and then it converts into uh, the disembodied and embodied energy levels. He may touch upon that. So these are his main areas. So Emory Taylor. So for me, Emory Taylor was somebody who has looked at it to very very originally, and he has a very logical way of explaining things, and he completely argued perfectly. Uh, and I have not seen that perfect argument for anybody. So it was very appealing to me because that's what I was looking for. And then can do mathematics after that. So it has to have a good basis, and I think he has a good basis. It all seemed to be working out, the actual levels and quantization and everything, which is so there's no real assumption per se, and that's a good aspect. Uh, so I
Okay,
think
thank
I
you,
will leave
Rajan.
to
I think you
Emory
should
Taylor.
give,
Yeah, thank you.
you should give the
Emory Taylor to
so that we can hear
Emory Taylor to explain more
something
about this.
shifted in the presentation style. Maybe can be corrected by responsible. I don't know who is doing it from you all. That we see Emory had side with his presentations sheet. So Emory, are you sharing presentation already, or
no? I haven't put it in there, but I can. Let's see.
It's always a bit tricky with this tool here but in the end it works.
Will we use the share screen one?
Yeah, you need to one way or another.
Under the bottom you see mute stop cam. In my thing it shows mute stop cam settings present. So you have to press the present button.
And you need to just present your screen or just an individual application. But I share usually the screen, it's easier, and then you get this recursive effect.
Yeah, exactly.
Once you're full screen, it goes away.
1 second.
At the very bottom, below our all our images.
Just hold on a second. I think I have to have this thing already up. Let me find it.
If you have multiple screens, it's difficult to see. We can't see then the other screen, only your primary one. And,
I know. All right. This should just hold on a second.
It's always the same. Take your time. It's the tool.
Shouldn't this one get bigger? There we go. Okay, now it should. Well, wait a minute. Present. Share the screen. I don't see mine in there.
Not yet.
Although it should be in there.
Yeah, then entire screen, and then click on the screen. When you see your entire screen, click on that, and then click share.
Okay. Well, I clicked the share, but it doesn't seem to want to do anything.
Is the share button, it needs to illuminate first before you can use it. So to do that, you have to click the image of your screen in that little box, and then it should turn blue, and then you click it. Do you get me? You select the image of the screen that you want to share by clicking on it, and then it should turn blue, I think. And then you click on that on the share screen.
Share me, my Mac version brings up share screen or share individual files or share video file. And sharing the files does not really work well when I do that, so I always share whole screen. And then you have still the trick with the virtual screens you might have from Teams, and this and this and this are all screens from the point of the tool, which makes it really difficult to choose the right one.
I agree. I had the same problem. When I use window or something, it doesn't move. So I had to go back there so that you can see the movement of the slides.
Conceptually, the Teams is doing that very, very well by now, not initially, but this tool is in a web browser limited to the sandbox issues typical tools like that have. And as you've seen on the other machine, wasn't unable to get the camera running despite I have allowed it. So there's always something with that tool.
Yeah, Emory, if you check chat, the private chat, I just, you know, so you click present first, then share screen, entire screen, click on the image of the screen, and then click share. That should be the right steps.
Yeah, I'm sure it is, but I'm doing those things, but it's not showing me the one that I have.
Well, you know what? If you could send us the image, I can share it, and you can talk over.
Hard as it is, you might reboot on your machine because sometimes it's the only thing.
It might be the internet, because I had to use the cell phone to get the damn thing working.
Oh yeah, that's right.
Well, how can I send it to you?
Send it to Rajan, because you have his email, don't you?
Yes.
Yeah.
Well, I sent it to him.
Oh, Rajan, you already have the image, so could you just share it on your computer, and Emory can get started on his presentation?
Okay. So
I sent you the updated version.
Okay. Let me check. PC.
All right, it's saying your browser has blocked your screen. Click the screen icon in your address bar to allow access, then reload the page.
Okay. That sounds a bit odd, but give it a shot, I guess.
Firefox or something sandbox art for users, but it's possible to do exactly what it says depending on the type of browser you have. But as you cannot show us your screen, we cannot help you with that. So that is really I
guess another issue is he
has it in his email. I sent it to him. It was either today or yesterday. It says updated. Says new updated tour.
Yeah, I can actually pull up from your. Yesterday you sent me the new one. I can actually pull up from there. Yeah, let me try that.
it's the email that says new updated tour.
Oh yeah, I have that now.
And it should be in there.
Yeah. Okay, so let me pull up that. Hopefully I can pull up in the share.
Because if I close this screen, then I'm going to have to turn the cell phone back on for whatever idiot reason to get this stupid thing to run.
So let me see. Let me see
I don't
the
want to do
entire
that.
screen.
Let me take this one out.
Yeah, there we go. That's looking good. If you
can you see? Can you see?
Can you embiggen that?
Can you
make
see?
it bigger? Full screen, maybe.
Yeah, that's
bottom right hand corner, Rajan. Bottom right, or would that be?
Oh yeah, I can increase bottom right.
No. Keep going to the other side. Further to your right. No, or your left then. Sorry, yeah, that button. But you need to zoom out now because you're too close in.
Oh, okay.
So you escape out of that. Just press escape, I think.
Oh.
Click out of that menu, press escape.
Okay, let me see that.
Oh, there you go.
And then you have to increase.
Yeah, you need to make it a bit bigger. Don't delete it.
Okay.
I don't think so. Just click out and press escape. Yeah, and now make it a bit bigger, maybe, was it? What size? That's enough. No, it's probably too much. No, way smaller than that. Smaller than that.
Readable. Let it stay. Just go ahead. We can read it.
Yeah, that's fine. Thank you.
That? Okay.
Perfect.
Okay, sure.
Is that how you want it to be?
Good to you.
Just start your presentation. You can read it fine.
Yeah.
Okay. Trouble is all right. Hold on a second, because I'm not able to see it correctly.
Oh.
But I have the picture myself.
Oh,
so
well,
I can just
that helps.
I can just look at my picture. I don't have to look at your picture.
Yeah, exactly. That makes sense.
Okay. If I can get it to enlarge itself here. There it goes. Now I should be able to just go up and down with the picture. Okay. Now, actually, this is an updated version. This isn't the one that was used at the conference, so it's going to look different to you, Christopher. And, right. So what's the new person's name here? Christian. Okay, I'm going to talk about discontinuum physics. And it actually comes from Einstein. In 1954, he wrote 3 letters. And in the 3 letters, he speculated that physics cannot be a continuum physics, that it has to be a discontinuum physics. And he speculated that what needed to be done was the continuum concept had to be tossed out, and what he meant as tossed out as being fundamental. It's still usable, but it's not fundamental. And he wanted to also toss out space and time and differential quotients. But since I'm writing the conceptual foundations for discontinuum physics, I'm not going to talk really about any math, so I'm going to ignore the part about tossing out the differential quotients. And if you're tossing out the continuum concept in space and time, then obviously you're tossing out relativity, and he knew that, which means he was tossing out, well, when I say tossing out, he means as being fundamental. It's still usable, it's just not fundamental. And that means you're tossing out special relativity, you're tossing out space-time, which means you're going to have to replace space-time. And you're tossing out length contraction and time dilation as being fundamental. And you're tossing out GR, which is general relativity, which has that theory of gravity in it, you're also tossing that out as being fundamental. And then in the letter in the third letter that he wrote, he's saying, now I'm stuck. I don't know what to do. Now that I've tossed all those things out, I'm stuck. Well, he didn't realize that in 1916, which was a year after he published GR in 1915, he writes this book to explain relativity to first-year students at university, and he's explaining what a continuum is, and he uses what he calls a marble tabletop thought experiment. And in the thought experiment, he's walking across the tabletop, and he says, I don't have to jump from point to point, because for a continuum, between any 2 points, there's an infinite number of points. So all I have to do is just walk across the tabletop. But in 1961, another version of his book comes out, and before he died, he had added a fifth appendix to it. And when you read that fifth appendix and you couple it with that tabletop thought experiment, it's easy to realize that what he actually did was, unknowingly, he introduced a quantized two-dimensional discontinuum geometry. And that geometry does exactly what he wanted to do in 1954, which was make the continuum concept so that it's not fundamental. So when he was telling the person that he was writing to, well, now I'm stuck, I don't know what to do, he was totally unaware that he had introduced that quantized two-dimensional discontinuum geometry. And we're going to use that geometry to get one of the realities. But I first want to, so I want you to know all that information before I talk about Newton. I'm going to talk about Newton now. He writes the Principia, and there's 3 versions of it that came out, or 3 editions of it. And between the first and second one, some scientists like Richard Bentley were saying that Newton was saying there was action at a distance and gravity was innate to matter. Well, in the Principia, he lists what the properties of gravity are, but in the very next paragraph he says, but I don't know what's causing those properties. So when he finds out that Richard Bentley and other scientists are saying he's claiming there's action at a distance and gravity is innate to matter, he writes to Richard Bentley and he tells him, don't be ascribing that to me because I'm not saying any such thing. Action at a distance is an open question, and gravity is innate to matter is also an open question. And he's again reaffirming the fact, well, I don't know what's causing those properties. And essentially he says you have one of 2 choices. It's either something physical, which he believes it is, he just doesn't know exactly what it is, or it's something that's non-physical. And he doesn't believe in that, so he doesn't want that one. But he tells Bentley, since I don't know what it is, the reader of the Principia has to make a choice. It's one or the other, and you have to make a choice. And in the Principia, he uses math, but he uses it in a special way. And when this problem about people claiming he was saying certain things that he really wasn't, he decided, well, I'm going to make it clear that when I talk about a force, I mean a mathematical force. And the reason he means that is because he wants you, the reader, to make the choice. Is it something physical or non-physical? And when he talks about a point, he's talking about a mathematical point, and it's the same reason. He wants the reader to make a choice. It's either something physical or non-physical. And he meant on the framework of absolute space and absolute time. And nobody actually did that. Along comes Einstein, and he's really using space and time together. But I've already told you that in the end, just before he died, he decided those weren't fundamental. that being, what? That being the case, you're now still left with those other three realities: the mathematical reality, the physical reality, and the non-physical reality. And because Einstein's tossing out the continuum concept as being fundamental, we want to be a little more technical. And the correct name is continuum reality, and in parentheses, physical reality. And the other one is called no continuum reality, and in parentheses, non-physical reality. So that's how you get the first three of the five realities. We just need two more. And there's been 10 foundational papers about discontinuum physics that have been published. So I'm going to have to take shortcuts, otherwise I'm going to be talking way too long. So the shortcut that I'm going to take is I'm going to use Einstein's quantized two-dimensional discontinuum geometry. And you got to remember, he was walking across the marble tabletop. So what he has is he has the atoms of the marble tabletop, but they're not touching each other. So there's an immaterial space between them. And the atoms, of course, are, since it's the marble tabletop, they're all exactly the same. So we're going to say that they're quantized. And the space between these atoms, which is in material space, those spaces are all exactly the same size, but they're not the size of those atoms. So we're going to say that they're quantized. And then we're going to take a quantized two-dimensional discontinuum geometry line segment of these alternating material and immaterial things. And we're going to call that line segment, we're going to call it discontinuum reality. And in parentheses, we're going to call it quantized reality. And that gives us the fourth of the realities. And then we have to go back where he was saying that special relativity can't be fundamental. We have to replace space-time. And this is done in a particular way in the second paper. And I'm going to just take a shortcut and tell you that in order to get the replacement for space-time, you have to have an unlimited disembodied energy. And from that, you're going to get two different energy fields. One of those energy fields is energy that's embodied in matter. That's, I know in physics is called bounded, but the papers are actually not for people who are physicists, so I call it energy embodied in matter. And the other one is energy that's not embodied in matter. And these two discontinuous energy fields, they come together. You never have one without the other. And they come such that they're actually part of each other. You can't take them apart. And that's the replacement for space-time. And that UDE that it came from, since if in this scheme of things that we're doing right there, if we let the energy embodied in matter represent a physical reality, and we let the energy that's not embodied in matter represent a non-physical reality, then the thing that they actually came from, which is the UDE, since we don't know really much about it or what it's actually based on other than that it's unlimited disembodied energy, we're just going to give it a name. We're going to call it no reality. And so now we have these five realities. But they're, as you should suspect, they're not going to play nice with each other, because the mathematical reality that Newton was using was based upon the continuum concept. And the continuum reality, which is physical reality, is also based on the continuum concept. But the other reality that Newton had isn't based on a continuum. That's the no continuum non-physical reality. And to have that fourth reality that we already made, which is the discontinuum reality, which is quantized reality, to have it match the reality, the material spaces and the immaterial spaces, they have to be part of each other, because the replacement for space-time, you're having the physical part, which is the energy embodied in matter, and the non-physical part, which is the energy not embodied in matter. They come as part of each other. So that discontinuum reality, it has two components. And one of the components is actually called limited continuum reality, which is physical reality. And the other one's called limited no continuum reality, which is non-physical reality. And they come as part of each other. So the discontinuum is in fact embedded in the fact that they're part of each other. So you have two realities. Well, let's see. You're going to have the no continuum reality, which is the non-physical reality, which came from Newton. It's one of the two constituents of that discontinuum reality. So you have over here, you have realities that are actually based on a discontinuum, and then you also have that no reality. But over on the other side, you have two realities that are based on a continuum. And because of that, they're not going to play nice with each other. And what we want to do is we want to create a table of realities and see if we can use it to make predictions. So what we're going to do is we're going to assign the mathematical reality and the continuum reality, which is physical reality, we're going to assign it to a conscious mind. And the other realities, we're going to assign them outside the conscious mind. And what this leads to is when you're looking around at the room you're sitting in, what you're doing is you're looking at continuum reality, which is physical reality. It's a real reality, but it's not fundamental. You don't see reality in its fundamental form. And the way I explain that is you have to be able to find food and water. And if you're evolving to the point where you can find food and water, you're not going to evolve to the point where you're going to see the realities that are applicable outside your conscious mind. Because what's going to happen is, well, if you see subatomic particles, the only thing you're going to see in front of you is a bunch of subatomic particles. So now how are you going to go find food and water? And I'll tell you about an experience I had after I had a stroke. The stroke damaged my eyes and it damaged my brain. And I was walking down the street after the stroke and I heard this bird flying above me and he was squawking really loud. So I looked up to see the bird, and in the sky, I see the grass and the trunk of the tree, and the bird flies right through them. And I'm thinking to myself, well, this can't be right. Something's wrong here. So I called my doctor's office, and I actually spoke to the nurse, the doctor's nurse, and she said that your eyes and your mind work together to form the images you see. Your eyes have been damaged and your brain's been damaged, but they will work together and they will eventually work it out. And then you won't see the tree trunks in the sky anymore. Well, my eyes and my brain did start working it out. And another thing that happened to me is I was going to this math class, and it was in this room, and it was made of these concrete blocks. And if you've seen concrete blocks, they all have patterns on them, but none of the patterns are exactly alike. Well, when my blind spots are on my right-hand side. When I walked into the room, I looked to my left, and my eyes saw the patterns on all the blocks over there. And I had not actually looked to my right where my blind spot, both of my blind spots are. And unbeknownst to me, my mind had picked out just one pattern on one block and stuck that pattern on every block over there. But I hadn't yet looked over there. So when I looked over there, what I saw was, and it happened really quick, but I watched it happen, is every one of those blocks had exactly the same pattern on it. And then my eyes and my brain started putting in the real patterns. So in like a second and a half, I watched every one of those blocks change to the pattern that was actually on there, and not the fake pattern that it had picked from the other side of the wall. And according to the doctor, this is a natural thing that people have strokes. Not everybody has, because there's another thing, part of it, I think they were calling it lazy eye. If you've had a stroke and have a blind spot and you have lazy eyes, then you'll actually see those patterns change. But if you don't have the lazy eye, it just changes them all at one time. So I became aware of the fact that, you know, your brain and your eyes actually work together to form the images that you see. So if you think about the fact that you've evolved to the point where you can find food and water, then you can understand that your mind is stripping away, because outside the conscious mind, those two realities come together. The continuum reality, which is physical reality, and non-physical reality, which is no continuum reality, they come together. You can't ever take them apart. But when you're looking at it, your mind just strips that one out, and now you're looking at just the one. But it only exists in your conscious mind. It doesn't exist outside your conscious mind. So you're seeing a real reality, but it's not a fundamental reality because your mind has stripped away that other reality. And now you can actually form a table of realities, because you can put the mathematical reality and the continuum reality, which is the physical reality, inside your conscious mind, and you can put the other three realities outside of your conscious mind. And now you can use the table of reality. You can set up a table of realities, which you're looking at, and now you can see if you can make some predictions. And the first one I looked at was the star. If that star were to collapse in upon itself, what would happen? Well, it would move up the table of realities. And as you move up the table of realities, what happens? Different realities, as you move along, are the ones that are applicable to the star. And eventually you cross that arbitrary point of 0.1 mm, which is here being used to divide the microscopic from the macroscopic. Once you cross over that line, the continuum reality that Einstein based general relativity on is no longer applicable. Instead, that other reality is applicable, and now you can make a prediction. And the prediction is GR is going to break down. It's not going to be usable when it gets so small, but it's never going to go to there being a singularity. So those are two predictions you can make right there. And there's other predictions that you can make, but now I've explained how I got the table of realities and what the table of realities is used for, and that you can use it to make predictions. So basically, that's my presentation.
Very good. Okay, so any questions for Emory there?
Rather a comment from my point of view. You constructed, Emory, a lot of naming convention, and I remember, what is the right English word? Not deeply, but I can fully understand what you are going through to express things that are not obvious in standard wave physics books. When I invented ice-space theory, I resorted to the Lego paradigm because in the Western world, at least, we sometimes, or most of us, play with it Lego stuff. And Lego has the intrinsic abilities to be discrete, because you either have a Lego fit in a piece of a baseboard or it doesn't fit. You can, of course, play with it shifting in around, like floating above the base blobs. But the game of Lego has to be played by fitting them into the blobs. And if you do that, you have multiples of n discrete fixed positions for your Legos. And that gives exactly a discontinuum, because either the Lego is in the position n or in n+1 or in n-1 or whatever. When you approach that more mathematically with less words, then probably you have to remove the zero, and you remove infinity, which are all concepts just also in the brain of mathematicians, which just does not exist. And why do we know that? Because we have found out that everything in our material world is based on quanta, and that alone atoms and electrons. And whether you believe in these or not is more a religious problem, but if you are at least a little bit scientifically inclined, you will surely have seen these things in electron microscopes and the like, and are not negotiating the obvious away. And when you do that, and you shower every morning, hopefully, then you will think, this is a cool shower. But then you should halt time for a second. All the water drops around you come to a logical halt, like when you stop a pause button on a film, and you think, what I'm doing here? I have opened a vent where H2O molecules, H2O, so water molecules of 2 hydrogen atoms and 1 oxygen atom come out in a combined electromagnetic flood, and the magnetism prevents they even touching my skin. My hair and the skin is also electric, and none of these molecules will ever touch your skin, literally not. And nevertheless, with a little bit of soap and stuff, and more or less a chemical reaction on your skin, you get managed to think you shower. But what you essentially do is you're raining Lego pieces on top of your skin, and that somehow cleans it. And every scientist knows that when he showers in the morning, because every scientist knows the HO2 molecules are real and they are quantized. They are countable. They are no way continuous in any way. And still, when it comes to their day jobs and they run into that, and they do all the integration stuff, they do differentiation stuff, which only works when you have zero and infinity. And here you have the real problem. When you abolish the zero, you abolish with that the mistake of zero, abolishes the problem of infinity once and for all, and everything is countable. And it counts from 1 to n, and not from 0 to something. That changes a little bit of your math, but not your problems. It just means that when you do an integration math, like relativity does, or sometimes quantum mechanics does, it is the approximation and not the solution. And the exact solution is the integer summation equation of that thing, which is called undersum and oversum and all that mathematical stuff you do when you learn integration. It's just flipping the coin around and say it's the same thing. It's just the exact one is the integer, my friends, and not the continuous one. You don't get different results at all, but you get an understanding of what the hell goes on. Because if you don't believe that, cool, but then please stop showering in the morning because it won't help. It doesn't even touch your skin. So what we're talking about. And this is the real psychological problem that needs to be solved. And the psychological problem is when you tell that people, they know that in the morning when they shower, but they forget that a second later when they're at office and still continue using their relativistic equations, which work so well that they don't want to give up on that. Because if they want to give up on that, they had to relearn everything they learned from school and restart from scratch. Well, I tell you, I had not to do that because I never studied myself. I'm an autodidactic person. I'm an IT expert, and I come from pixels. I come from bits and bytes. So I never had to forget anything of that shit because I never learned it in the first place. Of course, I know how to do integration, differentiation, and mathematica and everything, but it's not the point. The point is I have no psychological resistance to Lego, whereas all others in mainstream have. And when you, in your way of Emory, this is really a tough thing to overcome the people by words. I believe you need to switch from words to math and just tell them, go away, get rid of the zero, go away, get rid of the consequential error of infinity, take a Lego piece, do multiples of integers and make physics with that. Then everybody comes and tells you, hey, Emory, that is not possible. And then they tell them, Christian told you, you can calculate constants of natures exactly that way. And only that way, because there is no alternative theory on calculating constants of natures. So if you have the only theory of doing something, it's moot to argue if it's wrong or right. It's at least something, where others have nothing. And that makes the Lego model the preferred one in quantum area, because the last time I looked, quantized means in pieces of multiples of something. And what current mainstream physics is doing is really evil. It quantizes when convenient, and it completely ignores quantizations in other ends. Like they say, Planck constant is quantized. what did they do to the scientific world in 1905 around? It did do that the ultraviolet catastrophe, which was a completely wrong prediction that a baker in a bakery in front of his oven would, well, evaporate in 1 billion degrees every morning, and that obviously doesn't happen, and it bakes its bread and we can all eat it, okay? So something was wrong in the ultraviolet catastrophe theory. And then Max Planck came and said, okay, let's quantize the Planck constant. I don't like that, but let's do that. What happens? And suddenly you get the proper curve of the infrared distribution of the oven. It gets a peak, and then it's soft, goes out. And it's only one quantization. Now we have the proof of quantization of time in I-space theory. And what does that mean? If you accept mainstream, you have h quantized, the Planck constant. But Planck constant is volt-ampere second squared, so you have 2 times a quantized second in there. We have the golden ratio ampere quantized in there, which gives you the volt. It happens to be that the electron charge in numerical units in I-space IQ unit system is just golden ratio ampere times 1/6961 I-space seconds. And if you multiply that with 2 times 3 times 6961 I-space volt, so by a number of 6 essentially, you get the Planck constant in I-space IQ units. If you do the E²/h calculation with that numbers, you suddenly get a very surprising result, and namely that you get the correct lab measured value of the quantum Hall resistance up to 11 digits. And all we input is golden ratio as a value, which is exact, and 2 times 3 times 6961, where 1 is just 2 times 3 times 1, and 1/6961 is just the quantum of time. So we put nothing in it, get everything out, okay? That already shows that you can calculate the other 50 constants of nature that way, and that should give everybody in mainstream a kick in the ass to say, wait a moment, we have to look on different things than we currently do. So all the convenient cosmological mathematics to do quasar rotations and whatever there is not wrong. They have to just understand that they are approximations only, and the real thing is quantum. When I started I-space theory, I wanted to get rid of quantum mechanics, literally, because I was belief, and that was just my belief. You start with something, that all that canceling of infinity and minus infinity out of sums is mathematical bullshit and has to be eradicated. And I was in the strict belief that Albert is right. And now we end up after 20 years of I-space theory. No, sorry guys, Albert is completely wrong. Relativity is completely nuts, like as you say, Emory. And the quantum theory, in fact, is not nuts. It is as close as could be. It is just using the wrong math to get precise. But the principles of quantum theory, including EPR and all its effects, are undoubtedly experimentally proven. And you can always make a theory as what you want, but for me, the last word is the experiment. And in case of I-space theory and constants of nature, it's just a digit precision of the measurement. And that is a perfect fit for 50 constants of nature, up to 9 to 12 measurable digits. The most precise one is the Rydberg constant. And here comes the interesting conclusion, and I don't want to bore you with that, but there is a phase change going on in 10 to the power of minus 13 meters from LEGO to LEGO Duplo, in the sense that you have a very fine granular continuum. It is not a continuum, it's also LEGO, but a very, very fine granular continuum. This is what is perceived as a continuum, but is none. And then you have this LEGO style subspace, I call it, which is your second reality. So I might get different because you need a wording convention. I completely understand that. So I resorted to the LEGO team. So what I say in summary is that your ideas about the space-time are very, very close to that what I-space is saying. Everything is discrete, and you have to find a way to communicate with the rest of the world in the experiments. And you found a very tough one, a harder than I have perceived way. My way was easy, and said basically to everyone, sorry for that, fuck you. If you don't believe that, then you can read it in 20 years in the newspapers, and that's it. So because I have only a finite amount of time to express myself. And when someone is strictly against I-space theory, you say, so be it, yeah? Then learn later. But experimental evidence doesn't come and go, it comes and stays. And that means once it's falsified one of your ideas, you have to let loose and take an optimized theory. Now, with I-space, I have the sheer luck that I cannot optimize ice-based theory. It's integer. It's either completely correct as is or completely wrong in the sense of completely accidental. And I started with the values 20 years ago, and not a single of my papers have ever been revoked. Not a single of my calculations has ever been refined because I don't need to, because I cannot. It's either completely correct or bust, and that's it. And that's what I make believe that the iSpace is the way to go. But in the end, iSpace is just a different name for your ideas, Emory. And it's not, I read your stuff in the internet as far as I could comprehend from the logical idea. And saying a non-continuum, discontinuum is just a prosa problem of naming things. But from the logical idea behind, you're completely correct. And this is what I can tell you. It's completely correct, just saying it in a different way. And hence, this is why I love this text, because an idea which is stupid at first sight is not at all stupid when viewed from the right angle. And when viewed from the right perspective, suddenly a lot of things make sense. And constants of nature were not accessible in mainstream physics because they had no idea how to calculate them, up to the point to say it's completely impossible. Well, completely impossible took me 25 years, but it was not completely impossible. And that's the main thing to communicate here. You have to persist your ideas, you have to stick to them and massage them into the rest of the world until they bleed, and that's it. Because in the end, you win and they lose. Because when you're right, then all the others have to correct their values and yours is stayed. And the simpler your model is, the better. It's also interesting that you have a transition here in 0.1 millimeters, because I also see that in iSpace theory. I think that is the range going from quantum to what we perceive as real in your world is the continuum-based theory. So I would bring your words in the wrong order, I think. But this is interesting because this seems where the double slit experiments start to fail when objects greater than 0.1 millimeter go through them. There's ongoing experimental support for that in the University of Vienna. And maybe they have bigger molecules than 0.1 millimeter to the interference experiments there in the future, and then that would go up that value. But I doubt that it would go up to the range of, say, a human of 2 meters and throw the human through the double slit and it would still work. So there is a limit there. And that limit has to do with the iSpace predicted phase change at 10 to the power of minus 13 meters, where essentially everything from a pseudo-continuum goes to really Lego Duplo style complete discrete geometry. Completely discrete. And as a completely discrete geometry cannot move in the sense of a classical incremental movement theory in integration math, you have to have a way to, like a film shows you also a discontinuous thing when you watch the film. It is a photo after the photo after the photo with a certain frequency in front of your eyes. And that makes you believe you're looking at a film, but you're looking not at a film, you're looking at a discrete sequence of photos. And your brain is doing the rest, as we rightly said. When you look on the wall, you see patterns, move the eyes. All that is completely clear to me why that is, and probably more clear than most others you talk to, because they will not take you seriously, Emory. But I take you seriously because I can completely understand you. Completely.
Well, I'm glad that you do.
Sorry, can you repeat that?
So are there any other questions? Rajan, or
yeah, I just want to say that that's very nice to hear what Christian has said. That I think we agree, and that my thing also shows intrinsically quantized. Only thing I have not calculated, but I would think that I have calculated partly Emory's discontinuum length 10 to the minus 26, but that's an estimate. Because when you actually do, that's why I want to do the complete thing and then calculate and then probably include Christopher's space, the 4-dimensional space. So I'm coming to that. So then I want to scalarize everything. And then once everything is scalarized, then calculate based on that. I think that will be more meaningful and see where all these numbers lie. It could be in the attosecond instead of Planck. Planck is just the upper limit of the theory, but actual thing may be much smaller than that. I would think.
I find it also intriguing that the string theory in the direction of Christopher is experience has the same number of dimensions I conclude from purely logical reasons from. So the string theorists calculated in the beginning 26 dimensions. When I'm correctly read the books, then it was 10. Now it's 11 with the brain theory. But the 11 from the M theory, as clever as it is uniting all the other wrong string theories together, is basically error correction by a very clever mathematician to have a brain instead of lines, because lines are non-physical. You need to have objects of size 1. So the ICFAS theory, don't forget that, doesn't have dots. It has cells. And the cell has a unit cell, and this is 1, 1, 1, and not a dot, a mathematical one at 0, 0. This is bullshit. It exists only in your brain. And if you have cells, the minimum cells you can make Lego-wise is 6 around 1 cell. You cannot do less.
Right.
Edges. And you can do 8 around 1.
The brains are actually cells, or if we looked at them as cells, it might be a better way to go about it. Less error correction. Yeah, it's interesting. So Rajan, your comment is, yeah, I think we got your comment. I have a few questions. We can come back to you if you like. So just quickly, Emory, if you could summarize the 5 realities. I have mathematical reality, physical reality, matter-bound energy reality, and non-bounded energy reality. I think they're connected. So that seems like we have 4, but then is that just 3? Or yeah, just summarize them quickly for us.
All right. The first one is mathematical reality.
Cool.
And the second one is continuum reality, which is physical reality.
Yeah.
The third one's no continuum reality, which is non-physical reality. The fourth one is actually the no reality. It's the one from which the replacement for space-time comes. And then the third one is discontinuum reality, which is quantized reality. And it has 2 components. It has continuum reality, which is physical reality, and no continuum reality, which is non-physical reality. But they're part of each other. You don't ever get to take them apart. Your mind, when you're looking at around the room, your mind is stripping that one reality out of there. So you're just looking at the continuum reality. But outside your mind, they come together and can never be taken apart.
So the matter-bounded, matter and energy, or energy and matter.
Well, that's the replacement for space-time. It comes from the UDE, and you got to use some work by Einstein and Infeld. But anyway, one of them's, there's 2 energy fields. They're discontinuous energy fields. One of them is an EED field, which is the energy that's embodied in matter. One of them is the DED field, which is the energy that's not embodied in matter. And again, they come together. They're part of each other. They're not separate, and they can't be made separate. If you try and separate them, they revert back to the UDE.
Embedded in matter is something called the ether, where everything is embedded in. If the ether is material, which Einstein removed wrongly, completely wrongly, because the ether is real, it was just the Michelson-Morley experiment type, which they interpreted up until today completely wrong, because the Michelson-Morley will not work in vacuum. And the Michelson-Morley does work. Like look at the paper of Declan Trail and others who have made electronic experiments clearly detecting absolute speed in a certain direction of our solar system with respect to cosmological overall structure in the galaxies. Right. So that means clearly that the quantum vacuum that Emmanuel has done has an immense energy density of that.
So magnetic matter-bounded energy and not matter and energy and matter, and the other one, they're taken together, they're no reality, which is another one of the realities.
No, so isn't that just working?
No, that's just a replacement for space-time, and that's the depth field, and it's on the left. Let's see, it's on the left side of the table of realities. Everything that there is part of the depth field. It's either energy embodied in matter, or it's not energy embodied in matter.
Okay, so just to recap then, the first one's mathematical reality, second one continuum physical reality. Third one, non-physical continuum reality, which is what exactly? Just define that.
The third one is no continuum reality, which is non-physical reality.
Okay, but in a way, like define it like concretely.
Well, when you tell me what non-physical reality is, then I'll define it more concretely.
Okay, yeah, fair enough. But like, how did you arrive at it?
I express it in the form of a metaphor, and if you look on the table of realities, it's what's applicable to a subatomic particle, and that's what I was telling you about Schrodinger's cat thing. There's the scientist, there's the cat, there's the box, and then the entire mechanism.
Yeah.
That's supposed to, be the atom that decays and the hammer that breaks the vial and the gas that's in the vial. Where we're just lumping all that together as the mechanism. Well, the scientist, the cat, the box, and the mechanism are all made out of atoms. Yeah. Those atoms are all made out of subatomic particles. The reality applicable to the subatomic particle is no continuum reality, which is non-physical reality. Yeah. So all of the subatomic particles in that setup, all of them are thinking the exact same thing. They're thinking, I'm the only particle that exists. I'm at the only place that exists. That place has no size, and time is not elapsing. There is no past, and there is no future. There's just that moment in time. And that's the way I describe it, is by using metaphor.
Yeah, that's it's a very beautiful concept. So, but then the fourth one is quantum reality, isn't it?
Yes.
But how is that different then from the other? Because the third one seems to contain quantum and large scale stuff. Is it all mixed together? So then the fourth reality just deals with the quantum
third one?
stuff? The third one being no continuum, non-physical reality.
Yeah, that's okay. That's one of the two constituents of discontinuum reality. That's one of the two constituents. One. The other constituent is the continuum reality, which is physical reality. So physical reality and non-physical reality come together, and you can't take them apart.
And that becomes non-physical continuum, non-continuum, non-physical reality. I'm a bit confused about how these
reality that's based on, well, it has to be based on a discontinuum, because you have two realities that are literally part of each other, and you can't take them apart.
Excuse me. Another time we'll sit down and I might work out a kind of a diagram that's more that I can understand quicker by just looking at it or something. The moment I'm a little bit confused, I don't want to spend like all day trying to figure it out now. But we can come back to it at another point.
Well, see, the discontinuum reality.
EPR, you mentioned EPR on your diagram, and EPR is a little bit counter-experimental, proven to what you say, that time is at halt for an individual atom. That is essentially not true, because it's spinning. So wherever it is spinning in, it might be a zero-time thing statically, like a Lego piece has no time, but the Lego piece overall can spin in something.
Well, that's not
over an axis.
That reality is not for an atom. That reality is for a subatomic particle.
Yeah, okay, but
but see, you're viewing a subatomic. Well, all right. For quantum physics, that's actually a mathematical reality, because they're using a probabilistic reality. And when you
experimental truth, it's not just a mathematical realistic thing. EPR is real, experimentally proven, non-negotiable.
No, listen.
I think it's a question of
you're thinking about it in the wrong way. I'm thinking about it in terms of reality, just realities, because we're looking at the table of realities.
Yeah, I'm not thinking reality every day. I have to raise children, have money, and all these kind of very real. And in that sense, if I have an experimental result, I accept a theory which explains it, and there might be theories which explain only a part of the overall reality, which is true for the most theories, by the way, including ICFAS. ICFAS is a very narrow, very, very narrow edge where it explains everything perfectly, but it's not a TOE. It doesn't tell you how things are from A to Z. You can take the base of that theory and build your own model for that. You can calculate with that, but everybody can construct its own theory.
Emory,
you're mistaking something here. The mathematical reality is a real reality. Just as continuum reality, physical reality, it is a real reality. We're not saying they're not, we're not saying that they're not real.
Calculating things, because calculations are mathematical for sure, and mathematics is not necessarily calculating on the reverse, but typically we associate.
I'm going to show you. I'm going to show you how it runs astray, but you have to let me tell it to you. The mathematical reality, when they put the particle, which is actually a probability distribution, when they put that thing in a box, and we can use Schrodinger's equation, we can use the general Schrodinger equation where it has kinetic energy, potential energy equals total energy, and the wave function is evolving smoothly and continuously through space and time. When you're putting that in a box, you're actually putting it in like an energy well. Well, you should notice that there's something wrong. Because if you look, you're not letting me finish the explanation. You got to let me finish the explanation. On the table of reality, it tells you that in order to have separability, you have to have a reality that is not actually applicable to a subatomic particle. That energy well has separation because it has one side of the well, another side of the well, the space between the sides, and then outsides. These are all separate things. So what you're actually doing is you're taking one reality, it's a real reality, and you're putting it inside of another reality. It's a real reality, but it's not the reality that's applicable to a subatomic particle.
I'm not criticizing. I don't want to interrupt you. All I'm saying is we're not so far away than you think. It's just my wording is different than your wordings due to my historic definition of ICFAS-like stuff is very different from your world. I just suggest that you...
you see, I'm not saying that they're not real realities. They are real realities. That's what I'm saying. They are
drifting a little bit too much into metaphysical things if you're doing that, because I want to keep the mind off. Maybe you don't want to keep the mind off and put that into your model, but I try to do step one before step two, and depending on what you want to achieve, there may be the completely correct path or not. And I'm trying to do things like be as conservative as possible, close to that what the rest of mainstream physics is doing, while strictly being able to show where they got wrong and where they take the wrong path. And when you have too many just verbal aspects, in the sense that it has nothing to do with your physics, really nothing. It has just to do with what names you choose to describe them. Then it's like Christopher said, you get confused. And then it's no need to do that.
That's true. I like, diagrammatic things that I follow, but the thing that, it sounds like when you're talking about mathematical reality, you're kind of going into like Platonic, the Platonic realm.
Well, I already explained. It's because the discontinuum and the continuum, they can't play nice with each other because they're completely opposite things. So we're shoving one over into the conscious mind and we're leaving the other one outside the conscious mind.
Oh, okay.
But that doesn't mean they're not fundamental. Well, it means it's not fundamental the way you're doing it, but they're real realities. I'm not saying they're not real. They are real realities. We've just shoved them over into the conscious mind.
Right.
Clarify. I think, like I said, if I may clarify, like I said, the domains of reality, like space and time, like I mentioned, they mix them together, but you cannot mix them together. In the same way, these five realities exist by themselves, but you cannot mix them together. Then you get a totally different picture. Like he said, you cannot put, the thing into the box, then you are changing the domain of reality. So that mixing, you are comparing apples and oranges type of thing.
I understand. Yeah. Oh, it's
well, see, what I was going to explain is, if you look at these realities and understand what you're doing, you quickly realize that the collapse of the wave function isn't actually a real thing. All you're doing is translating out of one reality and into another reality. And the thing you're referring to as a collapse of the wave function really is just a depiction of the fact that you've translated out of one reality and into another reality.
Right. That's okay. So you're parsing the information. So
they're real realities, but we've just shoved them over into the conscious mind, is what we've done.
Yeah. It's very interesting. It's a very evocative concept. So I'd just like to know, though, you mentioned that there was a difference between this image is updated compared to the old one. Is it a major change, or is it?
Well, let me look at it. I got it here. I have to look at it.
So we'll have to look at
it. In section 2, it says the MR domain, which is the mathematical domain, and then it has that little one with the astrea. Then down below, there's the one with the astra, and it says probabilistic reality of quantum mechanics is a mathematical reality. Yeah. That's been added. But there's paper, the 12th paper, all of the entire, a lot of it gets updated, so that the final version is even different from the one that you're actually looking at.
Okay,
but since I didn't talk about that one, I didn't use it. So when I went to update the one, it was the diagram that was for the conference. Well, I updated it. Now I don't have the old one. Okay, so you have to look at the updated one, which wasn't used at the conference.
Okay, no problem. So I'm not sure if I should ask about the particles being separated in their own little bubbles for now. But I would like to ask about the black holes singularity. So
yeah, you can't have it.
Why don't black holes have a singularity, according to your prediction?
Because see where the star is on the table of realities? No.
No. Where? Oh, yes, I do. Sorry.
Okay. Now, see the arrow to the left that's pointing towards the star?
Yeah.
That's telling you that you can actually use mathematical reality and continuum reality, which is physical reality. Yeah. Now, remember, we shoved them into the conscious mind, but you can actually use them as though they were applicable outside of the conscious mind because of how large the object is. But if that star begins to collapse upon itself, you're going to go up the table of realities. And when you cross over that arbitrary chosen 0.1 mm, then that mathematical reality, which is Einstein's general relativity, is not going to be applicable anymore. And if you look over on the left-hand side, the closer you get to a subatomic particle, the reality is changing into no continuum reality, non-physical reality.
Yeah.
A singularity.
It is a singularity.
Well, in order to have a singularity, you have to have separability, and you don't have that. So it's not going to go. What you need is you need the replacement for general relativity, and we don't yet have that replacement.
Okay. So,
and I believe that is based.
It goes all the way to the point where that their singularities can't exist. What if it just goes?
Was it breaking up?
Yeah, you were breaking up a bit. Yeah.
Yeah.
It was a bit difficult to hear you. But so I don't know if you want to continue. Yeah, go ahead.
When you get down to near a subatomic particle, the reality that's applicable is no continuum reality, non-physical reality. And you don't have space, you don't have time. So all that stuff that you're talking about that's being forced into the singularity, well, you can't think of it that way anymore. You have to think of it in terms of no continuum reality. And you got to remember, in terms of no continuum reality, there's no size and there's no time elapsing. So there's not going to be a singularity.
Yeah, okay, I get that. So that's
need
fine.
The replacement for general relativity, which I believe is an algebraic version of Einstein's quantized two-dimensional discontinuum geometry, and we don't have that. So I
find it interesting the similarities between your theory then and the Ohm hypothesis, which I didn't really get into that aspect of the hypothesis in this presentation, but in a previous one I had talked about it. And also there's another so in the previous presentation I was looking at is it Holton-Arp's anomalous quasar redshifts. So there's, he found that quasars have a really high redshift, so they appear to be really far away from us. But he took photographs, I'm sure you might have heard of this, of galaxies that are quite relatively nearby to us, and the quasars are beside them, and you find like a bridge between the two objects, which suggests that they're like on the same plane. So so this called into question cosmological redshift. So he was kind of sidelined a lot. His theories weren't, I mean, obviously he was referenced and stuff, but he wasn't like given this grand platform by astronomers to kind of talk about his findings and his research. So that's a bit unfortunate, but I think he's being taken more seriously now these days, and astronomers are sort of distancing themselves from their distancing of him, which is kind of interesting to watch, but that's how it goes. And then so you have, so like my solution, their solutions are like, well, if we stick a black hole in front of the quasar, and a quasar is supposed to be a black hole anyway, then that could explain why it seems like it's being further redshifted. But that doesn't explain like all of the quasars, because that would be a highly odd thing to occur. But in my model, basically what I have is that, also another additional fact I should mention is that time dilation of the quasars, so this is considered another kind of confirmation of Einstein's model. But so in order to solve the problem, I have the quasar is kind of everything that sits on the hypersphere in the Ohm model is indented into the sphere. So that's the curvature of gravity, if you like. But a quasar, which is a black hole, is highly indented. So it's actually closer to the projective light source, and therefore its projected shadow, if you like, onto the tangent plane is stretched out. So it appears more redshifted than it actually is. And then for the time dilation aspect is that the further you go up towards the projection point at the zenith of the hypersphere, the more time slows down. So the closer your body is, like the further up it is to the top, the slower down it will be, because it's projecting from, instead of projecting into the point of the tangent space that correlates with where it is positioned on the hypersphere, it's moved up. So it's now going to be projected into a different point relative to it. So it's going to appear like it's moving slower than it actually is, sort of thing. So that, I feel, kind of merges a bit with what you're talking about as the star collapses, it goes up the table of realities. And it's very similar to what I'm saying, that as the star collapses and the gravitational well gets tighter and tighter, it will move up the side of the, further up towards the projective point. So there seems to be a connection there, even if it's just geometric or whatever, I don't know, or linguistic.
Well,
is it a,
right.
I want to ask.
Well, let Emory come back on that point. He might have something to add, and then you can go ahead, Rajan.
Well, see, I was going to talk about the gravity. See, everything's part of the depth field. That's what everything is. And a distortion of the depth field, because we're replacing space-time with the depth field, a distortion of the depth field is gravity. But what's happening when you get down to the size of a subatomic particle? What's happening is that particle itself, which is just a distortion of the depth field, and since gravity is a distortion of the depth field, the particle itself is the gravity. Okay. And of course, it doesn't act on its own self because, well, it is the gravity. So it's kind of hard to explain, but you can see that if you're saying that gravity is what's crushing that star down, the smaller and smaller it gets, the more the star itself becomes the gravity. It's not something crushing it anymore. The star itself is that gravity.
Yeah, well, I'm not sure about that specific issue, but I mean, there is the other point that you mentioned about, you know, if we get a particle as the only particle in the world, you know, and if there's no time, there's no space, like that's very interesting, again, from the Ohm hypothesis point of view, because of this point at infinity, which is also equal to like the smallest size possible, if you like. But it's odd because so we can imagine like, you know, continuum reality, and all the atoms or the subatomic particles are sitting next to each other, or so it appears. And then you zoom in on it into the non-continuum reality, past the arbitrary line, and it becomes the only point, or the only particle in the universe. And that's very interesting to me because geometrically speaking, that's what can happen with stereographic projection. So we could have the particle at the bottom of the sphere, and everything's packed in close together. And then by rotating it 180 degrees and reprojecting it, that particle will be infinitely far away from all the other particles in the universe. And it will also be at one and the same time at the smallest point in reality, which is way up the top of the zenith of the hypersphere. So there's like zero extent, no space up there, but also at the same time infinitely large, because it will exist around the perimeter of the entire universe. And because of the time dilation that I mentioned, as we go up the sphere, there will also be no time. So I can mathematically describe that part of the model, you know, because that was one of the criticisms I think Christian had. So I don't know if you're interested in expanding on that.
Well, see, the whole reason I I sent out letters to, I think it was either 200 or 150 physicists.
Wow.
Telling them about Einstein's 3 letters, where he's saying the continuum concept can't be fundamental, and you got neither space or time. And because, well, most people aren't aware of the letters, and I was looking for somebody, because I'm not that good with the math. And the way I explain it, let's say you and I are on a spaceship, and Dr. Iyer is there, and there's the pilot. And the pilot leans over and says to us, hey, we're going to crash unless somebody figures out this calculation, and we're all going to die. Well, I might get it right on the 5th attempt. He's going to get it right on the 1st attempt. Which one do you want doing the math? Because if you have me doing it, we're going to die. So my math isn't very good. So the whole reason this isn't expressed with any math is because I'm not the guy you need to be dependent on doing that. So my search was to find somebody who would do it. And, well, he's one of only 3 or 4 people that responded.
Oh, great. And so how many of those 3 or 4 are working on your...
Well, the others decided that they couldn't figure it out from just a diagram.
Okay.
Well, I can't give you anything. I can't give you anything other than a diagram. That's all I can give you. And so
yeah. Well, another time we should work together.
If you can't figure it out from a diagram, then I can't help you any farther than that.
Yeah,
because
well,
you can figure out what diagram I'm going to give you.
So, there's multiple ways. Like doing diagrams is also sort of a different skill that you can learn. You know, and there's multiple different diagram ways. So I could sit down with you. We could work out some different methods, and that would, I think, make it more clear than if you're going to show it to other physicists in future. But yeah, so well, that's all.
Yeah, and see that what I'm doing is laying the conceptual foundations. Somebody else has to lay the mathematical foundations because I'm not good enough to do that job.
Yeah, but it would probably.
So that's what I was saying. Like, what I've really done is really meant for first year people who are just out of high school. It's not really meant for physicists because I'm laying the conceptual foundations, not the mathematical foundations.
Yeah,
I'm really not capable of doing the mathematical foundations.
Yeah, that's no problem at all. That's completely understandable. I was always in that headspace as well for years because I didn't have any mathematical background, and I was coming up with ideas and I was like floating them, and I was hoping that someone else would pick them up and fill in the gaps, you know. But that approach didn't work for me. But since then, I've kind of gained more mathematical insight, and I've also found more, shall we say, concrete theories. And now, like, if I see your work or someone's work, and I think, yeah, that I can like work with that concept, or you know, then I have no issue working out the maths behind it because I've already technically done it. It's just the same thing that I've already done.
Well, you can certainly have a go at it.
Yeah,
you know, I can get you from the two-negate state to a antimatter asymmetrical universe. And if you read papers 6 through 10, it gets you to the antimatter asymmetrical universe. But of course, there's some math in there along the way. But doing more than that math.
Okay, that's interesting.
I'm just not going to be the one doing it.
Yeah, I think I also have a theory of antimatter asymmetry. It's part of the same own hypothesis. So, well, that would be interesting to me to find out, because if they're the same thing, then this is the same model, but just expressed in a different way. But if they're different, then that's obviously going to be a problem, because then it's then one of us is wrong, or you know, or both of us are wrong. So that's it. That's very interesting.
Well, you can send me an email, and I can. Unfortunately, all you're going to get is those papers that have been written and published, and some pretty diagrams. That's what you're going to get.
But Rajan's been working with you, hasn't he, on these papers? And has he been have you been contributing maths in that sense, Rajan, or has it been more?
Well, no. What he does is, if I need to use math, I send it over so he checks it and makes sure that I didn't foul the math all up.
All right, fair enough. Yeah. That's good. Yeah, Rajan would be good for that.
But one of the things I'm thinking is that the rank, I was talking about the rank, right? The rank, I think, is matches with this table of reality. I mean, I had to derive some more, but I think the scalar, the lower rank.
He does keep telling me he's working on it and trying to get it there. But you know, I'm not good at the math, so how would I know? I mean, he could tell me anything, and I would say, okay. You know?
Yeah,
okay.
the rank of the tensor matches with the tabular reality. But there are a couple of more, like we talk about the gravity, right? The gravity, okay, in the case of gravity in the black hole, you have the gravitational lensing that can change the redshift, for example. So the point singularity may be true, actually. The big singularity may be wrong. The point, a point, like Christian says, you cannot have zero. So that is a singularity. So it's actually a singularity is a point. Point singularity may be correct. Okay, so that makes it quantized and everything. So in the case of in the case of the black hole, a singularity may not be there, but there could be a point singularity. That's what I am coming to. So which
Okay.
means that there's a minimum thing that makes it observable. Like you cannot have gravity without particles, right?
Well, see, that's what I'm telling you is when you get down to there, the thing you refer to as a particle is the gravity. There is no particle.
Yes.
That's the gravity.
Yeah.
Okay, that's something that I didn't
gravity,
fully understand that point, but it could be true. I think, you know, with things like that, I probably would need to see more maths, but I think also the maths needed probably to describe that would be outside of my interest, even, you know, because it might get into, but it probably wouldn't get into Einstein's formulas. So, because by the sense of it, you're saying that they don't apply there. So it would have to be some other kind of mathematical formalism or something. But
well, I've been just assuming that it's the quantized two-dimensional discontinuum geometry, but I haven't seen anybody produce it yet.
Is that just the Lorentz transforms, like, of motion? You know, those, you know, the where you have time on the axis, y-axis, and space on the x-axis, and then you have the Lorentz transform?
Well, you'd have to go look at the very first paper and read through it.
Oh, okay. Yeah, that's fair enough. I haven't actually, I haven't spent a whole lot of time researching your material, which is odd because usually I would read up beforehand. Okay. I suppose I've just been a bit distracted or whatever. So maybe that's yeah. I'll tell you what. I will go and research I'll read through the first paper, first couple of papers, and then
it's only the first paper.
Okay.
It's not any paper after that, because after that first paper, I divert away from there and start heading for the table of realities, and you can see there ain't no math on it.
All right. Okay.
So only the first one would well, in the second paper, I replaced space-time and the what is it, the length contraction and time dilation. So there's some math in there, but it doesn't have to be there. I just put it there to make physicists happy, but it doesn't even have to be in there. But the first one is the only one that deals with the quantized two-dimensional discontinuum geometry. None of the rest of them do because, well, I don't know what it is. I don't have it.
Christopher, let me add some closing words. I need to leave. I want to just give a second on commenting on last words of Rajan with respect to singularities. Rajan, long time people in your domain were, said your domain is string theory, relativity, and all that, which is not my domain. But I found out something about six-dimensional geometry of I-space, which I think is intriguing. When in the simplest way to visualize that, you have a Möbius band, and a Möbius band is a piece of newspaper which you cut off as a long string of 1 meter. So rotate one of the sides by 180 degrees and glue it together. And the geometric implications of such a simple thing, where childs are playing with that, you can cut it together and get two rings which are interconnected and all kind of that, which you can read in newspapers. But the main thing is there is, in such a simple geometry, already no top side anymore. This thing has only one side.
Mm.
And you travel it, and you can do that by writing with a pencil on top of it. Take a pencil, write top, 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 and try to find bottom. And you end up, after you having completely curved the path, there's just top written everywhere because there has no bottom. Yeah? Mm. And that simple concept you can migrate mentally if you can. I can't do that. Really, I can see that geometrically, but you have to do that for yourself because 10-dimensional is not for everyone. Yeah? So this is just a 6-dimensional thing. A Calabi-Yau space, what is it? If you bend the right side to the left side of a Rubik's Cube and glue it together, and then you bend the front side and the back side of a Rubik's Cube and glue it together, you cannot in 3 dimensions bend the inside and the outside. So you get a torus with a hole inside in 3 dimensions after 2 bend operations. And the 3rd bend operations would mean you bend the inside of the torus with a hole to the outside of it, and that cannot be done in 3 dimensions because it's a closed thing, okay? Now, let's have God make it symmetrically for a moment and not prefer the x-axis or another axis you choose of your whatever. Kaluza-Klein chooses a specific axis. This is bullshit, okay? So don't do it 5-dimensional. Do it symmetric. So for the x, you get anti-x, which is not minus x, okay? Anti-x is x star. Mm-hmm. This is a different direction, like x and y are different directions, and spati are 90 degrees on top of each other. Just assume that in your brain for a moment. Then you have, with 6 dimensions, 6 true directions with plus and minus sign on each of the directions. And when you combine them Calabi-Yau style with the bending operation, just I showed you with the Möbius bend, you get a thing which is 0 size long because it has no outside. All the mathematics of Lego is still fully in place, so the I-space rules inside that thing fully work. So all the quanta operation work. But from a continuum point of view, it looks like exactly quantum mechanics predicts it. It has 0 size. Because it's not a single cell anymore. Even the cell is gone. Because the Calabi-Yau space has no outside. It has just inside. And oops, it's gone. It sounds like a mathematical trick, but the longer I think about it, it's not a mathematical trick. This is what really happens. And that is my kind of, not proof would be a too harsh of a way to say it on that mathematical level, but it is an indication why string theory with the 10 dimensions are completely correct, and that you cannot do it with 4, and you need 10. And
you can do it with 4. We had this discussion before, remember? I would have to go back and look at the video because it was about a year ago, but yeah, we pointed out that it is possible in 4 dimensions. I think your problem with that concept was, and you just mentioned it here again, was to do with without privileging a direction like an axis or something. But that doesn't really, I explained why that's wrong in a previous text.
But in 3 dimension, you cannot, even 4, you cannot make the electron to a true mathematical quantity. It will have its field there, and the field is not of 0 size. It's classical electron radius if you want it or not.
Well, I think that's different. That's a different issue. You've jumped from gluing the sides of a cube to the electron.
The electron is a torus which is glued 6-dimensionally in I-space theory. That is a matter of fact.
But it could be just glued 4-dimensionally, is what I'm saying.
No, it cannot be, because then God would prefer the x-axis. This is nonsense.
Why is that the case?
Because symmetry is must in physics. You cannot just have one direction to have easier math. Math is irrelevant. Physics is not irrelevant.
No, but I mean, you could be right, but I don't see why there would be this issue of like choosing the x direction or something.
All I'm saying is I find it intriguing that running the Calabi-Yau thing, the Möbius style, gets you in 4D classical field theory a dot, which is that what everyone else in the books in mainstream theory think the electron is. And this is giving a possible bridge between that, what mainstream is doing, I-space theory and string theory. If you look deeper than saying it should be 4D because the math is easier to do in that. So maybe, but has nothing to do with that, what I'm thinking.
Yeah,
I'm not saying you're wrong, Christopher. I'm just saying.
I kind of feel like, you know, that I remembered the sort of, what would you call it? The contention I had or whatever. So like if you have a triangle and you've got ABC written on the triangle, I think this is right. I can't remember, but you could go like, so A, B, C. So one, like 1, 2, 3 points on the triangle, but then you could count like 1 to 2, and then 2 to 3, and then 3 to 1, and then you can say, well, like that's 6 points, you know, because you've counted each point twice.
3 points in the edges of a triangle. I cannot see.
No, but what I'm saying, but like you go like 1 to 2, that's 2, 2 to 3, that's 4, 3 to 1, that's 6.
I cannot follow you geometrically here.
This is the point I'm making. This is what I'm suggesting you are doing by you're saying you're taking a 4-dimensional space.
Not what I'm saying. A Calabi-Yau space is
twice.
dimensional. Look on the theory of Calabi-Yau spaces. I talked with Wolfram about that, so I'm pretty sure it's correct what I'm saying.
No, but you see that what I'm pointing out. That's the way I feel. Like, well, actually, I don't even think you're using a 4-dimensional space. You're using a 3-dimensional space. Then you're counting all the dimensions twice, so to get a 6.
Correct. No, not counting them twice, but you're correct that I never use a 4-dimensional space.
Yeah, that's where you're going wrong. You should be in 4 dimensions.
No, 4-dimension is a space-time, and time is proven.
No, it's not.
I cannot do that because discrete means incompatible with theory of relativity.
Well, no, we're talking about 4 spatial dimensions. There's often a confusion there, like calling things 4-dimensional.
There are no 4 spatial dimensions in any theory I know of.
Well, I mean, there are, because you can go up to like different. Well, there are. There's Kaluza-Klein has
3 plus time is the root of x squared plus y squared plus z squared minus t squared, and this is relativity.
Well, whatever, but does it have an extra dimension or not? It does.
Yeah, t squared is the 4th dimension, but it's associated as a
Kaluza-Klein.
It should be plus t squared, and there are theories who do that.
Not in Kaluza-Klein, it's not. It's an extra spatial dimension.
Yeah, okay, then you have a probable theory with 4 true spatial dimensions plus time, and you end up Kaluza-Klein style one way or another.
That's what we're talking about. That's what I just said.
Okay, then we agree even. So I don't want to disregard that. It's just I'm fond of symmetries, and I think everything should be symmetric for, well, reasons. That doesn't mean...
Yeah, but I mean, you could have 4 spatial dimensions are symmetric, and then add in, like, time is not, like, a spatial dimension. So that's just
exactly, and that's why time is something different than a spatial dimensions. And the relativity has compromised that simple view to death, to put it mildly. That's why I believe relativity is complete bullshit, not just wrong, not even wrong.
I think, like I said, it's a mixing of domains of reality. You cannot mix like that. And that's the problem with relativity, like space and time. You problem units, so many other things that you just take it dt squared and then multiply by the speed of light somehow. So that you have to assume the speed of light is, maximum limit and everything. So there is a lot of fixing there. I think that's the problem. Not only mixing, but also fixing,
Is that we have to discuss offline maybe for a point. I need to leave now. I'm thank you so much.
I think we should wind up soon. We can have another day discussion of dimensions.
Yeah. We probably should do that graphically with help of Mathematica to visualize what I'm about and send that before
next
the
week. I think. Next week will you be able to come, Christian? Next week we can have. We'll see you next week, probably. Anyway, I will send out.
We will not have time. I know that for sure already now, but maybe the weeks after again getting.
Okay.
Okay.
Right.
Fair enough. Thanks for
Bye.
See you. Thank you, Christian. Very nice discussion. Yeah.
Okay, we should probably end this week there as well. Yeah. So.
Yeah. So next week we will catch up on that. We will continue with that.